Yes. Just give a reply whether all good. If you all can hear me speaking, just give a reply. Okay. So then we want to start the pending stories in optical instruments. Can everyone give a small reply? Whether all good, my sound, my voice, and all good. Just give a small reply. All good, right? All good. All good. Right. Okay. Right. Okay. Okay. We'll start. Okay. Right. Okay. Right. Uh, so then I think we have done some sections in lenses and we have small pending sections to be covered in lenses. Today we'll try maximum to cover all the theories related to lenses. That's our target. There are lots of questions to be done. Today our priority is completing all the theories in lenses. And if it is possible, we are going into the optical instruments. That is the idea. That is the idea, right? Okay. Now, already I explained that when I was explaining refraction of light through plane surfaces, I explained that real objects and real images and virtual images. Right, when you consider real images and virtual images, we know that when the light rays really converging to a particular point, then we said that at that point there will be a real image formed. When the light rays seem like converging to a point, then at that point, a virtual image will be formed. That idea I explained already. And we have done some questions also. Now, today we are talking about formation of real images due to virtual objects. Formation of real images due to virtual objects. That story. Right. I think I haven't kept space for that section in the tute. Therefore, take your notebook and if not, you can turn the tute and you can see there are some empty spaces. I have given some empty spaces in the tute. Right, in that tute itself, you can write down. If not, just take your notebook and just put the story, put the topic. Real images formed by virtual objects. Right? Real images formed by virtual objects. Okay. Now listen this idea very carefully. Listen. Now this time object is virtual. Till now we talked about real object. Real object means what? The object which physically exists. That's what we call as real object. For an example, I am a real object. All the objects that you see, all the objects that you are able to touch, they are real objects. Then give me a kind of example for a virtual object. Maybe when I'm looking myself by standing in front of a mirror, the thing that I can see through the mirror is a kind of virtual object. Real object means, remember, they are able to physically, they have a kind of physical appearance. They are really physically existing. Virtual means they do not exist physically. They form due to a kind of optical phenomena like reflection, refraction. There's a difference. If the object is real, remember that object is able to touch, that object must exist physically. If an object is virtual, that object is not physically existing. We are not able to touch that object. That is the idea. That is the idea, right? Okay. Now, story. Now, first of all, I will explain this idea formation of real images by the virtual objects. I will explain this idea by taking a convex lens. Right? Let's draw a convex lens. This is the principal axis. This is the convex lens. Right. Let's say focal length of this convex lens is a simple f. Simple f. Right? Just consider now, I only draw two light rays. Two light rays incident on this convex lens. Right? I'm drawing two light rays incident on this convex lens like this. Very careful listen. Very careful listen. This idea. I will draw the diagram first, then I will explain. Right. Okay. Okay. Now, don't think about this right side idea. Only think about there are two light rays incident on this convex lens. Right? Suppose if there isn't any such convex lens, very clear that when you extend these two light rays, if there is no such convex lens, the surrounding is only same medium, these two light rays would have converged exactly at this point. So we know that when light rays really converging to a point O, when light rays seem like converging to a point, exactly at that point there will be images. If the light rays really converge, the image will be real image. If the light rays seem like converging at that point, the image will be kind of virtual image. Now in this scenario, there are two light rays. These two light rays incident on this convex lens, right? Still, I haven't drawn the path of these two light rays after the refraction. When you extend these two incident rays, we understand that these two incident rays seem like converging exactly at this point, right? Still, I haven't completed the ray diagram. I only drew the incident two rays. I will draw the refract rays bit later. When you extend these two incident light rays, very clear that these two incident light rays seem like converging exactly at this point. Then we understand, sir, whenever light rays seem like converging to a point O, really converging to a point, there will be an image. Since these two light rays are seem like converging at this point, there will be a kind of virtual image. Now I will tell you, now I will roughly tell there will be a kind of virtual image. Later on, I will tell it as a virtual object. Okay. Exactly this point, there will be a kind of virtual image. Virtual image. Right. Roughly keep in your mind, there will be a kind of virtual image. That point is clear. That point is clear, not that much difficult. There will be a kind of virtual image. Okay, virtual something. Now, what will happen now after the refraction from these two? After the refraction from the convex lens, what will happen for these two light rays? Normally, remember, convex lenses converge light rays. That means convex lenses converging light rays. They convex lens bring the light rays together. So, if you draw the refracted two light rays, those two light rays going to be, those two light rays will going to be like this, right? After the refraction from this convex lens, these two light rays will converging exactly somewhere here, right? After the refraction from this convex lens, this light ray converging exactly at this point. Then, sir, when light rays really converge at a point, at that point also there will be an image. If the light rays are really converging, that image gonna be a real image. Now, so what did you mean by, in the beginning, the topic was what? The topic was formation of a real image by the virtual object. Now, very clear. Now, this ray diagram is very clear. There's a convex lens. There are two incident rays. These two incident rays, before the refraction, seem like converging somewhere here. Therefore, definitely, there will be an kind of virtual image form here. After the refraction from these two, after the refraction from the convex lens, these two light rays really converging somewhere here, definitely there will be a real image at this point, right? In this scenario, remember, we consider in the beginning these two incident rays, since seem like converging somewhere here, we consider the image here, right? That is what we call as virtual object. For this scenario, this one going to be the virtual object. Very clear. Very clear. It's a virtual image. That's clear. It's a virtual image. Very clear. But we are giving a name for this scenario. That is going to be the virtual object for this scenario. Then if you consider this as the virtual object, this one going to be the image. Finally, normally, what is the image after that reflection or refraction, after that optical phenomena? The final one is the image name. After the refraction from this convex lens, the finally formed one is the image. So definitely this one is going to be the image. We consider this one as the object, right? That is the idea. This one as the object, this one as the image. Since this is a kind of virtual something, that is going to be the virtual object. This is a real image. That's what we call as real image, that idea. How many of you understand what I explained here, students? How many of you understood what I explained here, students? Idea. Raise your hands, idea. Raise your hands, idea. What you do, draw this diagram quickly. This diagram quickly. This diagram quickly. This diagram quickly. This point mark it as point capital O. This point mark it as point capital I. Quickly. Point capital O, point capital I. Point capital O, that means object. Point capital I. Finish marking, raise your hands. Once you finish drawing, raise your hands. This is what we call as a virtual object. This is the real image. So this scenario creates a real image due to a virtual object. This scenario creates a real image due to a virtual object. That's the idea. Therefore, mention exactly at here. Virtual object. Virtual object. And this one is your real image. This one is real image. Real image. Mark this. And if this is the object, the distance measured from convex lens optical center to the object is object distance. And mark the U and V. The distance measured to the image from the optical center of the convex lens is image distance. Mark them. Mark them also. Mark object distance and image distance. Mark them also. Mark them also. So then this is going to be object distance U. Right? This is going to be object distance U. Arrow is right direction. Then what should be the image distance? From optical center to image, the distance. Image distance V. This is going to be V. This is going to be V. Right? That idea. Okay. Once you finish drawing, raise your hands quickly. Once you finish drawing, raise your hands quickly. Right. Quickly. Now below write down. A converging beam of light. A converging beam of light. A converging beam of light entering a convex lens. Entering a convex lens. If not incident a convex lens. Entering a convex lens. Incident on a convex lens. Entering a convex lens appears to converge to a point. Appears to converge at a point. Appears to converge at a point. Capital O. Point capital O. Full stop. Okay. Continue. So it acts as an imaginary object. So it acts as an imaginary object. So it acts as an imaginary object for the lens. So it acts as an imaginary object for the lens. For the lens. For the lens. Next point we can write down. The image is formed at a point where 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 the light rays actually meet. The light rays actually meet. The light rays actually meet. That is a real image. That is a real image. That is a real image. Okay. So now idea very clear. when these two light rays seem like converging at this point. So therefore, the image formed at this point is what we call as virtual object. The image formed at this point is what we call as virtual object. After the diffraction from this convex lens, these two light rays are converging at this point. That image formed at this point is what we call as real image. So you can consider this as the object, this as the image, object distance u and image distance v. That is the idea. Now, what about for a concave lens? Same story. When two light rays seem like converging at a point, if I draw a concave lens idea, same story. For a concave lens, same idea, same idea. Draw the diagram with me, with me. Right. Focal length of this concave lens is simple f. And there are two light rays incident on this concave lens, such a way they appear to be converging at a point somewhere here. Right? Focal length of this concave lens is simple f. There are two light rays incident on the concave lens. Those two light rays appears to be converged somewhere here. That idea. Right? Okay. So now these are the two incident rays incident on this concave lens. It is having a focal length simple f. Right? Before the refraction of these two light rays, seem like converging somewhere here. Right? Therefore, we know that when the light rays seem like converging or really converging at a point, exactly at that point, there will be an image. Exactly at this point, there will be an image. This is what we call as object. Right? If I ask you the characteristics of this image, we all know that this image going to be a kind of virtual image. This is what we considered as the object. So the object going to be a virtual object. Right? Do you understand? That exactly at here there's an image, but what we do, we consider it as an object, right? So therefore that object is kind of virtual object. After the refraction from this concave lens, these two light rays diverge and will exactly converge somewhere here, right? After refraction from this concave lens, these two light rays are diverging and converging somewhere here, right? They really converge somewhere here. Okay. Then when these two light rays really converge at this point, then we know that there will be an image that is going to be real. Why? Light rays are really converging at this point, therefore the image is real. That is the idea. So then we consider the image formed at this point as the real, the image formed at this point we name as virtual object. The image formed at here we name as real image. Object image, virtual object, real image. That is the idea. That is the idea. Then I'm marking this point as point capital O. Point capital O means object, right? So you mark this point is point capital I, image. Mention that virtual object, real image. Virtual object, real image. Mark that. Virtual object, real image. Mark that properly. Mark it properly. Mark that properly. Quickly. Virtual object. And then this one is going to be real image. Real image. Okay. So then if you mark the object distance and image distance, the distance measured from optical center to the object, that is going to be the object distance u. Object distance u. Right? The distance measured from optical center to the image, that is going to be the image distance. Simple. Simple. Right? Right down there. Right down below. A converging beam of light entering to a concave lens. A converging beam of light entering to a concave lens. A converging beam of light entering to a concave lens. A converging beam of light entering into a concave lens appears to converge at a point capital O. Appears to converge at a point capital O. Appears to converge at a point capital O. This acts as an imaginary object for the lens. This acts as an imaginary object for the lens. This acts as an imaginary object for the lens. Different virtual object for the lens. This acts as an virtual object for the lens. Full stop. Full stop. Next line, write down, next line. The image is formed at the point where the light rays actually meet. The image is formed at a point. The image is formed at a point where the light rays actually meet. Where the light rays actually meet. Where the light rays actually meet. If I repeat it again, the image is formed at a point where the light rays actually meet. That is a real image. That is a real image. That is a real image. Now, when we talk about today, we are talking about how to do questions when there are more than one lens involved in a question. If there are two lenses, how to do questions. In that story, you will understand. When I do that question, I will explain. Right? Now, what shall we do? We'll do some questions. Take your tute and start doing these questions. Take your tute. In the tute, we'll do question number 16, 17. 16, 17. Page number 35 and 36. Page number 35, 36. Start doing question number 16, 17. Start doing question number 16, 17. 16, 17. 16, 17. Raise your hands. How many of you started doing 16 answer? How many of you started doing question number 16 answer? Start doing. Now I clearly explained that now this one is going to be the object and image, object distance, image distance, focal length. You know how to apply lens equation for a given scenario. Then this knowledge is more than enough to do that questions. Start doing 16 and 17. Start doing them. Question number 16, they say what? A beam of light incident on a converging lens of focal length 20 centimeter seems like converging to a point O 10 centimeter from the lens. Right? Then exactly at that point only the virtual object exits. Object distance going to be how much? 10 centimeter. Find how far the rays actually converge from the lens. Right? Then you want to find image distance V. You want to find image distance V. Find the answer. Find the answer. Apply lens equation. Apply lens equation and apply sign convention. Then substitute the values and get the answer. Right? Same story. Same story. Same story. Question number 16. Hands up, how many of you substitutes? I'm in the substitution stage answer. So I'm in the substitution stage answer. I'm in the substitution stage answer. Right? I don't draw a separate diagram for that. I use this diagram and I apply the story. I apply lens equation. We know that lens equation. Lens equation, question number 16, 1 over V minus 1 over U equals 1 over F. Lens equation. Right? 1 over V minus 1 over U equals 1 over F. Apply sign convention. Apply sign convention. Right, they talk about a convex lens. Question number 16, a beam of light incident on a converging lens of focal length 20 centimeter. Right, and converging, seems like converging to a point O 10 centimeter from the lens. Seem like converging to a point O 10 centimeter from the lens means I know object distance 10 centimeter. I know F. They're asking us to find the point, the distance to the point from the lens where light rays actually converging. I want to find the image distance for the scenario. I want to find V. Now we can apply lens equation. The light rays are moving to the right side direction. Direction of light is right side direction. Then object distance and image distance both are in the direction of light. Direction of light also right side direction. Object distance also right side direction. Image distance also right side direction. Therefore, we know that the sign of U and sign of V both negative. If the distance is in the direction of light, its sign is negative. Therefore, U and V is also negative, negative. Since it's a convex lens, negative. Then this negative, negative, negative cancel out. Again, I'm getting 1 over V minus 1 over U equals 1 over F. If you cancel out these two negatives, you are getting again 1 over V minus 1 over U equals 1 over F. A substitute. Your target is finding V. I want to find V. I want to find V. I want to find V. Get the answer. Get the answer. I want to find V. My object distance U is going to be how much? That is 10 centimeter. Focal length how much? 1 over F. A focal length is that is 20 centimeter. Right? Substitute 1 over V. When you substitute 1 over V, you get the answer. Substitute 1 over V. Then minus 1 over 10, right side 1 over 10. Right? 1 over 10 minus 1 over 20. Right? Then common denominator is how much? 20. It's 2 minus 1. 2 minus 1. That is equal to 1 over V. So finally, you get that your image distance V is going to be how much? Your V is going to be how much? U is 20. Right? Right? Okay, you want to find V? Sorry, your U is how much? U is 10. Okay? Right? If I apply sign convention, convex lens minus, okay. 1 over V plus ni. Right? Minus 1 over 10. If I move the right side direction, it's plus, so plus 1 over 10. Right? Okay, my bad. Okay. Then 1 over V. Then if you take the reciprocal, V means 20 over 3. 20 over 3 means we know that 6.67 centimeter. How many of you got 6.67 centimeter hands? How many of you got that 6.67 centimeter hands? Centimeter. And do the next question also. Next one. Next one is about this story, simple story. Question number 17, as shown in the figure, a beam of converging rays incident on a concave lens of focal length 15 centimeter, such a way that it seemed like converging to a point capital O at a distance 10 centimeter from the lens. These converging light rays seem like converging at point capital O. Distance to the point capital O from the concave lens is 10 centimeter. That means your U is 10 centimeter, focal length is 15 centimeter. You want to find V. Same story. Apply sign convention. Same story. Same story. Get the answer. Definitely, when you are using lens equation, the next step must be applying sign convention. That is must. You must apply sign convention. That is must. 16 done. Then 17. 17 idea. Again, lens equation. Lens equation. Get the answer. 1 over V minus 1 over U equals 1 over F. Then sign convention. Direction of light is right side direction. In this scenario also, direction of object distance and image distance are in the direction of light. Therefore, the sign of U and V both negative. Minus, 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 minus. But concave lens sign is how much? Plus. For a concave lens, focal length is positive. Then done, I apply the lens equation, I apply sign convention, substitution. I want to find V only. I want to find V only. Minus 1 over V. Minus 1 over V. Right? And minus into minus plus. Object distance U is 10 centimeter, 1 over 10 must be equal to focal length is 15 centimeter. 1 over 15. 1 over 15. Right, what shall I do? I thought of moving minus 1 over V right side, and I will move this 1 over 50 left side. Then it's going to be 1 over 10, 1 over 10 minus 1 over 15, right? 1 over 10 minus 1 over 15, minus 1 over V right side means 1 over V. Must be equal to 1 over V. 1 over V. Find the answer. What is the common denominator for both of them? We can take 30. 30 as the common denominator. 30 as the common denominator. Then here's 3. 3 minus 2. That is going to be equal to 1 over V. Finally, when you substitute the image distance, that is going to be how much? 3 minus 2 means 1. 1 over 30 equals 1 over V. V equals 30. How many of you got V as 30 answer? How many of you obtained image distance V as 30 answer? V equals 30. Simple story. Simple story. V equals 30. That idea clearly. That is also done 30 centimeter. Right? Okay. Done. Right? Okay. So what shall we do? We'll do questions. Then there is one last, not theory. There are some important stories. Right? Go to the Tutan. Go to the Tutan. Page number. In the Tut page number. Right? In the Tut page number 26. Page number 26. Okay. Listen very carefully this idea. Okay. Page number 26. Okay. The last story. Right. Now this idea. How to explain? Okay. Right. Okay. Right. Listen very carefully what I'm going to explain now. It's a very important story. Okay. Right. Now just consider, now I am considering a convex lens. Consider a convex lens, right? Consider a convex lens. Okay, right. This is also another type of question pattern. Right. Okay. Okay. Uh, let's say now there's an object. There's an object. Right. Okay. There's an object. This object is object capital O. Then this is the convex lens. Just consider this object is kept beyond the focal point of this convex lens. Think like that. Don't think about formation of virtual images from this convex lens. Only think about formation of real images from this convex lens. Then very clear that this object must be beyond the focal point of this convex lens. That is clear. Let's say now this is a kind of screen. A screen. Normally we use screen to locate the image. Why are we using screens? To locate the image of that object. So this is a screen. A screen. Huh? Screen. Then when the object is at a distance of u from the convex lens, there will be an image exactly formed at the screen. Definitely we know that that image must be a real image, inverted, right, image. If I draw the image, that image going to be somewhere. Image will be formed at the screen. This is the image. This is the image. Okay, right. This is the image, capital I. I1. Let's say I1. Let's say I1. Right. Okay. Now what you do now, you are not changing the gap between object and the image. Object and the screen, sorry. You are not going to change the gap between object and the screen. Right? When the object is somewhere here in front of the convex lens, we realize that image of this object will be formed exactly at the screen. Okay. Right. Let's say object distance for the scenario, case number 1, object distance is u. Case number 1, if you measure the object distance, that is u. Object distance u. Right. If you measure the image distance, that is v. Is v. Right. Very carefully listen. We are not going to change the location of the object or the screen. When the convex lens is somewhere here, when the object distance is u1, then when the object distance is u, there will be an image exactly at the screen. So the image distance to the image is v. Okay, right. Now what you do, you are moving the screen now. So you are moving the convex lens now. Now see, now you are moving the convex lens away from the object, right? So when you move the convex lens away from the object, what will happen to your object distance? Object distance will increase. In the beginning, think like object distance is smaller value. Think image distance is a larger value. Roughly think that u is, for an example, 20 centimeter. V is, for an example, 50 or 60 centimeter. Then when you move the convex lens away from the object, we understand that object distance will increase, right? But you are not changing the location of the object. You are keeping the same object, the same location. What you are doing, you are moving the convex lens away from the object. Then we know object distance, little by little, object distance will increase. Okay? When you keep the convex lens exactly at this location, right? Same object. We are not changing the location of the object. Same object. Same object. But we notice that right, simple idea. Okay, once again, if I explain it very simple, we maintain object location and screen location same. Always remember that image is formed exactly at the screen, right? Image is formed exactly at the screen, right? When you keep the convex lens somewhere here at this location, when the object distance become u, you notice that there will be an image formed exactly at the screen, right? When the object distance is exactly u, you notice that there will be an image formed exactly at the screen, right? What you do, you further increase your convex lens. You are moving the convex lens away from the object, right? Then once you started moving the convex lens away from the object, now the image was formed at object distance u. Once you further move the convex lens away from the object, now that image disappeared. Now you don't see any image formation on the screen. Now, when you slowly, when you move the convex lens more and more away from the object, again there will be an image formed exactly at the screen, right? Do you understand what I'm telling? In the beginning, when the object distance is u, there was an image exactly formed at the screen. After you move the convex lens up to a certain location, again there will be an image formed at the screen, right? Okay. This time earlier, the image formed on the screen is a larger image. But now the image formed on the screen is a small image. A small image. A small image. Right? Small image. This image I name as I2. This image I name as I2. I2. Right? Okay. This happens, that's a pattern. Right? Again, unless you don't change the location of the object and the screen, right? When you move the convex lens away from the object, again you will have an image at the screen when your object distance becomes this v, right? Again, image will form on the screen when the object distance becomes exactly the previous image distance. That's the idea, right? Earlier object distance, let's say u, initial object distance, let's say u1. u1 is exactly u. When your u1 is exactly u, when your image distance exactly v, then we noticed a large image formed at the screen. Okay. Now, when the moment you start to move the convex lens, already formed image disappear on the screen. When you started to move the convex lens, already formed image disappear from the lens, disappear from the screen. Right? What you do, you more and more you move the convex lens from the object. again you will understand, again you will notice another image formed on the screen that is smaller size than the previous image. This happens, this formation of second image happens when the object distance is exactly the previous image distance. Let's say now your object distance is u2. When your u2 is exactly v only, the second image forms on the screen. Second image forms on the screen. That is the idea. That is the idea, right? Then see the idea. If I draw the u2, now object distance to the object. See the idea. Very simple. Now this is your object distance now. Carefully listen. Object distance, let's say u2. That u2 is, we all know that is equal to how much? That is now v. Now the object distance equals to previous image distance. Then what is the image distance now? That is equal to previous object distance. Right? If you mark the image distance, that is equal to previous object distance. Got it? Image distance, let's say v2. That is exactly equal to previous object distance. Right? That is the idea. So very simple. Very simple. Summary is very simple. What is the idea? The idea is when you talk about formation of real images for a convex lens, when we keep the object and screen fixed, we are not changing the location of the object or screen. So what we are doing when we are moving the convex lens from object to the screen, we notice two situations where image is formed on the screen. We notice two situations where image is formed on the screen. Right? Under case number 1, when your object distance equals u, right? Then corresponding image distance is v. Again, when your object distance becomes v, there will be the second image. That is the idea. How many of you understood what I explained, answer? How many of you understood what I explained, answer? Idea is clear, right? Okay. So what you do now under that golden point, right? Under that golden point, what you do? There are two golden points below the second golden point. Write down red color pen. Second golden point, red color pen. Write down red color pen. Write down. Write down. Write down. When real images are formed by a real object, when real images are formed by a real object, when real images are formed by a real object, when real images are formed by a real object placed in front of a convex lens, 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 and and if a converging lens is moved between, and if a converging lens is moved between, and if a converging lens is moved between an object and a screen, an object and a screen, an object and a screen that are kept at a fixed distance apart, 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 comma, comma, two distinct positions of the lens, two distinct position of the lens, two distinct positions of the lens, two distinct positions of the lens will produce images on the screen, will produce images on the screen, will produce images on the screen, will produce images on the screen. Right, okay. Now listen very carefully, okay. Then idea is very clear. When we don't change the locations of the object and the screen, if we are moving the convex lens from object to the screen, we noticed at two different locations, images will be formed on the screen, right? For an example, when the object distance equals to capital U, there will be an image formed on the screen. When the object distance is capital V, which is the previous scenario's image distance. When the object distance now is equal to the previous scenario's image distance, then also image will be formed on the screen. What basically happened is, previous scenario, case number 1, object distance and image distance, and case number 2, object distance and image distance, they are interchanged. That means previous scenario object distance is now scenario's image distance. Previous scenario's image distance is now scenario's object distance. That is the idea, right? That is the idea, very simple, right? And next important thing to be noticed is case number 1, the image is very larger image, but the case number 2, the image formed on the screen is somewhat small image. Especially if I tell you that previous scenario, the image formed on the screen is larger than the object. Now scenario, the image formed on the screen is lesser than the object. Okay, case number 1, if I do some stories, case number 1. Case number 1, linear magnification. Now we know case number 1. See the idea. Object distance what? Object distance is what? That is U. Case number 1, object distance is U. Image distance is going to be how much? That is capital V. Capital V or simply whatever. Image distance, that is V1. That is capital V. Simple V. What is the linear magnification of the image formed in case number 1? Linear magnification in case number 1, I marked it as capital M1. For an example, capital M1. Are the linear magnification capital M1 going to be image distance V1 over object distance U1? Capital M1 means what? V1 over U1. V1 over U1. Image distance is going to be V, object distance is going to be U. That means V over U. V over U. Capital M1 means what? V over U. Capital M1 means V over U. I take it as equation 1. I take it as equation 1. Now, when you talk about case number 2, second scenario, case number 2, now the object distance U2 is V, right? Now object distance U2 is what? V. Now the image distance V2 means U. Who was the previous object distance? Now it is the image distance. who was the previous image distance, now it is the object distance. That is the idea, right? Then image distance v2 means what? That is u. Okay. Then linear magnification for second scenario, let's say capital M2. Capital M2 means we know image distance over object distance v2 over u2. v2 over u2. Then capital M2 means v2 means u, u2 means v, u over v. Capital M2 going to be what? Capital M2 going to be u over v. Simple. U over v. Then you can obtain a kind of relationship between linear magnification in case number 1 and linear magnification in case number 2. From equation 1 and 2 we can write down. From equation 1 and 2 we can write down some ideas. When you do questions, these will be important. Right? Capital M1 means v over u. Capital M2 means u over v. Therefore, what can you say about capital M1 and capital M2? Capital M1 means 1 over capital M2. Right? Capital M1 means 1 over capital M2. Am I correct? Because v over u, right? You can do it. Now, what can write down? One can write down, if you did the reciprocal, 1 over capital M2. 1 over capital M2, that is going to be v over u. Then the reciprocal, 1 over capital M2 means v over u. Right? Then equation 2 dash. When you take equation 1 and 2 dash, you can write down. Equation 1 and 2 dash, you can write down. Capital M1 means 1 over capital M2. Capital M1 means 1 over capital M2, this idea. If not, capital M1 into capital M2 is 1, it's up to you. Capital M1 means 1 over capital M2. That idea important idea. The most important thing is remember this scenario. This is a kind of question pattern they can ask MCQs. Right? What is the distance between? Now I told you the distance between object and the screen is fixed. We are not changing the location of the object or location of the image. That is a fixed distance. Then what is the distance between object and the screen? Always u plus v. The distance between the object and the screen is, remember, always u plus v. Right? Next important story is the distance between object and the screen. Right? Always u plus v. Right? Remember, the distance between object and the screen is always u plus v. Always u plus v, that idea. That idea, u plus v. Also note that if I ask you, reply everyone, in terms of u and v, tell me someone, what should be the distance between these two locations of the convex lens? Reply someone. What should be the distance between these two locations of the convex lens? In terms of u and v, can someone tell me the gap between these two locations of the convex lens? Someone tell me. Someone? Can someone tell me that idea? Can someone tell me the distance between these two locations of the convex lens? Quickly. Tell me quickly. Tell me soon. Tell me soon. V minus u. Very good. See this idea. So now see. When you consider the distance from convex lens to the object is v. This is v. And here to here gap is. Here to here gap is distance from this lens to the object is u. This gap is u. This gap is u. Here to here gap is v. Then the gap between these two locations of the convex lens is v minus u. Very important. V minus u. Right? You want to remember summary is very simple. Right? In this scenario, what you want to remember is object location and the screen location. If not, image location remains fixed. But location of the convex lens varies. In the scenario 1, whatever the object distance, in scenario 2, it becomes the image distance. In scenario 1, whatever the image distance, in scenario 2, it's going to be the object distance. Right? Simply, object distance and image distance are interchanged in scenario 1 and scenario 2. Right? When talking about the image, right, two scenarios, the size of the image is different. Therefore, their linear magnification is different. their linear magnification relationship is M1 is equal to 1 over M2. Right, that idea. And also the distance between object and the image is always u plus v. The distance between two locations of the convex lens is v minus u. That is the idea, right? That is the idea, right? Now what shall we do? Now we want to copy this idea. I think in the tute, I have given that diagram. I have given the diagram, but better if you can do this diagram and if you can write down the stories there. In the tute, I have given the diagram, but one after one, not exactly one below the one. So therefore, what you do, take your tute and right. Where is that? Okay, in that page number 26, you can take that now. Page number 26, the topmost golden point. We are not writing anything. I think mistakenly on it is printed. Right, you can use that entire space and you can draw this diagram. You can draw the diagram, nicely mark everything. And case number 1, case number 2. Put here case number 2 when this ideas. One capital M1, capital M2 idea. Right. And write down, okay, after you write all the stories, you want to write down the distance between object and the screen is u plus v. Then the distance between locations of the convex lens is v minus u. Once you finish writing, raise your hands. Once you finish writing, raise your hands. Theory-wise, we have done everything. I want to teach you about compound lenses, how to find the focal length and power. That's a small story I will tell you at the end. Theory-wise lenses, that's it. Right? Once you finish writing, raise your hands. I think I have done everything properly. I took time and calmly, slowly, I have done everything properly. I take the given space nicely and nicely write on everything. Lenses theory finished. Only that compound lens, how to find the focal length for a compound lens and power. Small story, that's it. Finished writing, raise your hands. Now we'll do questions. Every question you will learn something new, right? Every question you will learn something new. We'll go to questions and we'll thorough it. Now I have put plenty of questions and I have put plenty of questions, right? But we'll give a try to discuss them, but can't discuss. There are lots of questions. Give a try. Give a try. Finished writing, raise your hands. Then we can go to next story. If you finished writing, raise your hands. Then we can go to next story. Finished writing, raise your hands. Genuinely hands up, whatever the theory that we learned regarding lenses, everything is crystal clear and every theory point we learned regarding lenses, everything is crystal clear and crystal clear. That's it. That's it. Now time to do questions. At the time now 7:20. 7:20. Then we are taking a break at 8:30 something. We'll take a break at 8:30 something and we'll now do the questions. Okay, take your tutor and start doing these questions. We'll do a few questions from this pattern. Then we'll go to the compound lens story and we'll do some questions. Theory wise finished. We'll do some questions. Right. Go to the Tudor page number 40. Page number 40. Page number 40. Right. Starting question number 49. Starting 49, then 50. Starting 49, then 50. Starting 49, then 50. Question number 49, then 50. Starting them. Starting them. Question number 49. The distance between an object and a screen is 9 centimeter. Distance between object and the screen is 9 centimeter. Object and the screen. That means U plus V is 9 centimeter. Then we can write down. U plus V is how much? 90 centimeter. Right? That's how you want to think. U plus V is how much? 90 centimeter. 90. Equation 1. Then what? Then what? When a convex lens was moved between them, a larger image was produced on the screen in the one case and a smaller image is another case. Find the focal length of the lens. Find the focal length of the lens. If the first image is 4 times the, right, find the focal length, what did I mention? Find the focal length of the lens. If the first image is 4 times as large as the second image. If the first image is 4 times as large as the second image. Right, this idea. This idea. Now what we can do, see the idea. See the idea. Now, case number 1, we know that the formed image is larger one. Case number 2, the formed image is smaller one. Right, let's consider now object height is HO. Object height is HO. Object height is HO. Right, same object, therefore both the scenarios, object height is same as HO. In the case number 1, the formed image height is, let's take it as H1. Case number 1, the formed image height is H1. Case number 2, the formed image height is H2. We all know that as I drew in this way, H1 is larger than H2. This image is larger than this image. Clearly, they mentioned in the question, find the focal length of the lens if the first image is 4 times as large as the second image. What can you say about the ratio of H1 to H2? First image is 4 times larger than the second image. H1 to H2 is how much? 4. H1 to H2 is how much? 4. Given data. H1 to H2 is how much? That is 4. What's your target? Your target is finding the focal length. Simple if focal length is convex lens. Anyhow, you want to apply Snell equivalence equation. Anyhow, you want to apply lens equation and sign convention. Right? This is the given data. This is the given data. You want to find simple if. That's your target. Give a try. Question number 49. Give a try. 49. Give a try. This is the idea. Give a try. Now we can write down linear magnification in terms of heights as well. Rather than writing linear magnifications in terms of object and image distances, we can write down them in terms of heights also. I will give that idea also. Right. Then linear magnification, capital M1, we can write down H1 to H0, right? Linear magnification, capital M1 means what? We can write it as image height is H1 over object height is how much? H0. Agree? This is, I take it as equation number 1 dash. Equation 1, equation Roman number, equation simply. I take this as equation simply. Linear magnification of this image in the second scenario. That is image height over object height, h2 to h0. Capital M2 means what? Capital M2 means we can write down h2 to h0. Equation simple B. Then what we can do, what will happen when you divide equation simple A to equation simple B? Let's give a try. When you divide them, equation simple A over simple B, in that case, equation simple A to simple B, we can write down capital M1 to capital M2, capital M1 to capital M2, that is going to be how much? H1 over H0, H1 over H0, the division H2 to H0, multiplication H0 to H2. And then we can write down that H1 to H2. We can write down H1 to H2 is how much? H1 to H2 is how much? H1 to H2. Height of the image 1 to height of the image number 2. That is equal to capital M1 to capital M2. This side also remember. This side also somewhat important. These are not standard equations. Just roughly remember them. Now get the answer. We know U plus V is how much? 90 centimeter. And they have given H1 to H2 is how much? 4. H1 to H2 is 4. Get the answer. Capital M1 means 1 over capital M2. Capital M1 over capital M2 means H1 over H2. How many of you found the linear magnification capital M1 over capital M2 hands up? If someone found, if anyone found linear magnification capital M1 or M2 hands up? Right, from the stories, if anyone found linear magnification capital M1 or capital M2 hands up? One found capital M1 or M2? Only one? Only one found? Now to do this question, I directly take these equations. Then easily, I directly use this equation to get the answers. There are different ways. Right, okay? Then we know that H1 to H2 means what? H1 to H2 means we all know that is going to be capital M1 to capital M2. I can write down H1 to H2 means what? Capital M1 to capital M2. So I can write down here capital M1 to capital M2. Capital M1 to capital M2. That is going to be how much? H1 to H2, that is 4. And we know that capital M1 means 1 over capital M2. If not, capital M2 means 1 over capital M. Capital M1 means 1 over capital M2. Capital M2 means 1 over capital M1. So I thought of writing capital M2 as what? 1 over capital M1. Simple. I can write down. Nice story. Capital M1 over. Capital M2 means what? 1 over capital M1. 1 over capital M1 means what? 1 over capital M1 means 1 into capital M1. Must be equal to 4. Right? Then we can write down capital M1 squared is 4. What is your capital M1? Capital M1 squared equals 4. Capital M1 going to be how much? Capital M1 going to be. I hope you all understood how I got this capital M1 to capital M1. I hope. Capital M1 squared equals 4. Capital M1 means 2. How many of you got capital M1 as 2 answer? How many of you got that capital M1 as 2 answer? How many of you understood how the way I obtained capital M1 as 2 answer? How many of you understood how the way I obtained capital M1 as 2 answer? If you have doubt, ask, okay? If you have any doubt, ask. Done? Okay, simple. Thereafter, easy. Ask. I told you, if we know the linear magnification, capital M1 means linear magnification of this scenario. Right? Apply a Lenz equation and try to involve linear magnification term in the equation. Then you will be able to get the answer. Right? Okay. Okay, get the answer. Now capital M1, see capital M1 means what? Capital M1 means image distance V over object distance U. I can write down capital M1 means what? Capital M1 means the idea V over U. Capital M1 is 2, 2 equals V over U, V over U. Substitute V, then V equals how much? 2U. Image distance equals 2 into object distance 2U. Right? I take this as equation number 2. There are different ways to get the answer. Equation number 1, U plus V equals 90. Equation number 2, V equals 2U. I thought of writing this I thought of writing this V in terms of U. Right? V equals 2U. Then U plus V means what? 2U. U plus 2U equals 90. From equation 1 and 2, I can write down. From equation 1 and 2, I can write down. U plus V means what? 2U. V means 2U. Must be equal to 90. Then U plus 2U, U plus 2U means 3U. 3U equals 90. 3U equals 90. U equals how much? 3U equals 90. Finally, my object distance is going to be how much? 90 over 3 means 30. U equals 30. Right? My U object distance equals 30. If my U is 30, what is my V? If my U is 30, V is how much? 60. Right? Simple. If my U is 30, U equals 30 centimeter. Then from equation 2, we can write down. From equation 2, we can write down the image distance V equals how much to U? V equals how much? 2 into U. 2 into 30. That means 60 centimeter. Since I know object distance and image distance, I can find the focal length. The scenario, I know U is how much? 30, V is 60. I can find the focal length. Case number 1, apply Lenz's equation. Now it's easy. Case number 1, Lenz's equation. Lenz's equation. Get the answer. Get the answer. Get the answer. How many of you got the answer? Raise your hands. How many of you got the answer? Likewise, keep on doing 50. 48. 48. Get the answers. Get the answers. So 1 over V minus 1 over U equals 1 over F. I apply sign convention also. Focal length for a convex lens sign is negative. Direction of light is right side direction. Direction of light is right side direction. Object distance is opposite to the direction of light, therefore positive. Image distance is in the direction of light, therefore negative. V is negative, U is positive. V is negative, U is positive. 1 over minus V, minus 1 over V, minus 1 over U, minus 1 over F. All the minus cancel out. 1 over V plus 1 over U equals 1 over F. Right? 1 over V. V value is how much? 60. Plus 1 over U. U is 30. That is equal to how much? 1 over focal length simple if. Common denominator is going to be 60. Common denominator is going to be 60. X1, X2. 1 no simple if. Then 3 over 60. 3 over 60 means how much? 60 over 3 means 20. F equals how much? F equals how much? 20 centimeter. F equals 20 centimeter. 20 centimeter. How about we started doing question number 50 answer? Started doing 50 answer. 50 started answer. 50 started answer. Raise your hands. How about we started doing 50 answer? Keep on doing. Don't waste your time. Keep on doing. You guys keep on doing. Don't waste your time. Don't waste your time. Keep on doing. That's it. Right? Question number then 50 story. A convex lens placed between an object and a screen produced an image 4 centimeter high on the screen. A convex lens placed between an object and a screen produced an image 4 centimeter high on the screen. Right, 4 centimeter height. Height of the image formed on the screen is 4 centimeter. Without changing the position of the object and the screen, when the position of the lens was changed, a 16 centimeter high image was received on the screen. Find the height of the object. Find the height of the object. Right? Let's say now in the beginning they mentioned height of the image formed on the screen is 4 centimeter. The second scenario, height of the image formed on the screen is 16 centimeter. Again, they have given this H1 to H2 ratio. Again, they have given H1 H2 ratio. It's a different story. Simple. H1 is how much? The first scenario, height of the image is 4 centimeter. The second scenario, height of the image formed on the screen is how much? 16 centimeter. 16 centimeter. Okay. So then what you can do, you can find H1 to H2 ratio. H1 to H2 ratio, you can find it. H1 to H2 is what? That is the M1 to M2 ratio. Right? Simple idea. Simple idea. Right? So we know that capital M1 to capital M2 ratio, that is going to be equal to H1 to H2 ratio. Then you can easily find M1 to M2 ratio. Okay. If you substitute capital M2 as 1 over, if you substitute capital M1 as 1 over capital M2, whatever, one can substitute capital M1 as 1 over capital M2. If one can consider capital M2 as 1 over capital M1, it's up to you. It's up to you. Now, then what we can do, right? Then capital M1 over M2 means what? 1 over capital M1. 1 over capital M1 means 1 into capital M1 must be equal to how much? Must be equal to H1 to H2. H1 4, H2 16. 4 over 16. 4 over 16. Then capital M1 squared equals 1 over 4. Simple. Hands up, how many of you got the answer? Question number 50 got the answer? Got the answer? Question number 50 got the answer? So still we are trying answer. Still we are trying answer. Still we are trying. I'll give some time. If you finish getting the answer, raise your hand. Doesn't matter right or wrong. Doesn't matter you got the right answer or wrong answer, completely all right. Once you finish, raise your hands. I'll give some time. Give a try. Give a try. I'll give some time. Give a try. Just give a try. Just give a try. Just give a try. Finished. If you got the answer, raise your hands. Right, 2 finished, 3 finished, 3 got the answer, 3 got the answer, 4 got the answer. Quickly get the answer. Get the answer. Get the answer. Get the answer. Done is simple, very simple story, sir. A very simple idea is here. What is the idea? Now capital M1 into capital M1 is 4 over 16. Capital M1 squared equals 1 over 4. Right? Capital M1 squared equals 1 over 4. Capital M1 means 1 over 2. Simple. Capital M1 squared equals 1 over 4. Capital M1 means how much? If you take the root both sides, capital M1 going to be 1 over 2. 1 over 2. So linear magnification in scenario number 1 going to be half. Now here capital M1 means not this scenario. Capital M1 belongs to this scenario. So okay. So now I want to find the object height. Then linear magnification means we can write down in terms of image height over object height. Right? Capital M1 means we know that. Linear magnification of the image means image height over object height h0. H1 value, I know that. H1 value is 4 centimeter. I want to find HO. I know capital M1 means half. Capital M1 means half. I want to find the H1 value. Sorry, I want to find the H0 value. Image height H1, that is 4 centimeter. That is 4 centimeter. Subject object height H0, that is 8 centimeters. Simple. 8 centimeters. Simple, done. Question number 50 done. How many of you started doing 40 answer? Started doing 40 answer. Started doing 48 answer. How many of you started doing 48 answer? 48 start answer. 48. 48. The 48, the distance between an object and the screen is fixed. When a convex lens is moved between the object and screen, images are formed on the screen for 2 positions of the lens. If the magnification of one image is 3, what is the magnification of the other image? 1 over 3. Right? If the magnification of one image is 3, let's say if your capital M1 is 3, the magnification of other image is how much? 1 over 3. Right? The magnification of one is other magnifications reciprocal. Right? If you consider capital M1 as 3, capital M2 must be 1 over 3. That is the idea. Simple. When you consider capital M1 as 3, the magnification of the other image must be 1 over 3. Why? Capital M1 equals 1 over capital M2. Capital M1 3, 1 over capital M2, subject capital M2. Capital M2 going to be 1 over 3. Simple idea. Then capital M2 going to be 1 over 3. I don't substitute and I don't get the answer. Directly I take it as capital M2 as 1 over 3. 1 over 3. Okay. What else? What else? What is the magnification of the other image? If the distance between the object and the screen is 60 centimeter, U plus V. If the distance between the object and the screen is 60 centimeter, U plus V, 60 centimeter. U plus V, 60 centimeter. Okay. Right. Find the distance between the above 2 positions of the lens. Find the distance between the above 2 positions of the lens. That means you want to find U minus V distance, because we know that the distance between the 2 positions of the lens must be U minus V, right? If not V minus U. If you consider V is larger than U, if you consider here V is, write this story also. If you assume V is larger than U, the distance between the 2 positions of the convex lens must be V minus U. right? Your target is to find this gap. That's your target. If you can find V and U separately, you can get the answer, right? You want to find the distance between the two locations of the convex lens. If you can find V and U, then you can get the answer. Try to find V and U. 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 Right? Ni? Capital M1 is 3. Simple. Capital M1 is 3. Ni? Capital M1 means capital M1 is larger magnification. This is belongs to this scenario. Ni? When you compare these two scenarios, larger magnification, we are getting a greater magnification in scenario number 1. We get a smaller magnification in scenario number 2. Therefore, M1 is 3. This is suitable for this scenario. That means what? H1 over H0 is 3. If not what? V over U. V over U is 3. I can write down capital M1 is 3. That means image distance V over object distance U is how much? 3. V over U is 3. Right? V over U, that is 3. Then what is my V? V is going to be how much? V is going to be 3U. Image distance is going to be 3 times the object distance. Equation number 2. Equation number 2. Now, what you know now, when you substitute instead of capital V, if you substitute 3U, you get the answer. From equation 1 and 2, you get the answer. From equation 1 and 2, right? U plus V means what? 3U. V means 3U must be equal to how much? Must be equal to 60. Then we can write down here U plus 3U, 4U. 4U equals 60. That means U is how much? Object distance how much? That is 15 centimeter. Object distance how much? 15 centimeter. U, object distance 15 centimeter. Then what is your image distance V? That is going to be V means 3 into U, 3 into 15 centimeter. That means 3 into 15 is how much? 45 centimeter. Right? Therefore, image distance V is how much? 3 into U. 3U. 3 into 15 centimeter, 45 centimeter. Right? Then I want to find the distance between these two locations of the convex lens. That's going to be V minus U. V is 45 centimeter. U is 15 centimeter. Therefore, V minus U is how much? V minus U means 45 minus 15. 45 minus 15 is how much? 45 minus 15 is how much? 30 centimeter. How many of you got the gap as 30 centimeter answer? 30 answer. 30. So that idea done. That idea also done. That story done. Okay. That idea also clear. Now what you do in that short note summary. In the tude summary write down. In the tude summary write down page number. Okay. Page number summary page number 27 summary. I have given 2 boxes. In that boxes you want to write down. The distance between object and the screen is U plus V equal U plus V. The distance between object and the screen equal U plus V. Next box you want to write down the distance between the distance between 2 locations of the convex lens equals V minus U. Right? Second box you want to write down the distance between 2 locations of the convex lens equal V minus U. That idea done. That story clear. That idea is very clearly not a difficult story. Simple. Then right. Okay. Now we'll do few more questions. Somewhat difficult questions also. Now starting question number 19 to 20. Question number 19 to 20. Page number 36. Page number 36. Question number 19 to 20. Question number 19 to 20. 90 to 20. Starting them. Start doing them. Question number 19, 20. Start doing them. Start doing them. Nineteen, 20. Then 20. 19 started answer. 19 started answer. 19 started. Don't waste your time, right? In this time, stay focused and learn. That's what we can say. Stay focused and learn, right? Be at that moment. Be at the moment and learn. Right? Be at the moment and learn. That's what I can tell you. Right? Question number 19. Idea, simple. Find the linear magnification of the image of a real object placed in front of a converging lens, right? Placed in front of a converging lens so that the object distance is half the focal length. So that the object distance is half the focal length, right? Okay. Find the linear magnification of an image. I want to find capital M of a real object placed in front of a converging lens, convex lens, so that the object distance is half the focal length. Right. Okay. Now, without drawing a ray diagram, normally most of the questions we don't do the ray diagram. Normally we draw a sketch and we mark the convex or concave lens and we mark the location of object and image for our easiness to apply lens equation. Right? Normally we draw a sketch and we mark the position of the convex lens, position of the object and image to get that object distance signs. U is positive or negative, V is positive or negative. Then we have a good clarity about our way that we are doing, right? But most of the time, without drawing a sketch also, you can get the answer. But till you practice, till you are very familiar with these questions, I advise to draw a sketch. Roughly draw a sketch. Roughly mark the location of the object. Likewise, roughly mark them. Question number 19. 19 idea. 19 idea. Question number 19 idea. 19. Okay. Now there is a convex lens. There's a convex lens. I don't know the focal length of the convex lens. I don't know. Let's take it as simple length. Focal length. Let's take it as simple length. And here is going to be the focal point. Focal point is somewhere here. Where is the object? Object is in front of the convex lens. It's a real object. Real object. Object is in front of the convex lens. Object is exactly at a distance half of the focal length. Optical center to focal point is simple length distance. The distance between optical center to focal point is simply focal length. Object is at a distance half of the focal length from the optical center. Right? Then we know object is in between optical center and focal point. Where will be the image? Image will be formed at the same side behind the object, virtual enlarged image. That story you know. That story you know. That story you know. Here is your object. Is your object capital O. Then when the object is in between optical center and focal point, image will be formed at the same side behind the object. Virtual enlarged image. If you want to mark the location of the image, you can mark the location of the image. Roughly. So when you mark the image and object locations, it will be very easy to, for you, it will be very easy to mark this, apply the sign convention for the lens equation. If you mark the locations of the object and the image, it will be very easy to apply the sign convention for the lens equation. It's a large image, okay? Sometimes you can't see it's a large image. Huh? Draw a large enlarged image. Draw an enlarged image, okay? Image is capital I. Image is capital I. Right. Okay. Then the object distance U. That is equal to half of the focal length f over 2. Object distance f over 2, half of the focal length f over 2. Image distance capital V. Capital V. So you want to understand object distance and image distance both are in opposite direction of light. Direction of light is right side. Object distance and image distance both are opposite to the direction of light. Therefore, their sign is positive, positive. Lens equation. So lens equation. Lens equation. 1 over V minus 1 over U equals 1 over F. Sign convention. Since I know the location of object and image, I'm going to apply sign convention for all the variables. I'm going to apply sign convention for all the variables. A convex lens sign is negative, and since U and V are opposite to the direction of light, they are for positive, positive. What's my target actually? I want to find the linear magnification of the image. I want to find the capital M actually. I want to find capital M linear magnification of the image. Therefore, better to involve capital M in the equation. There are different ways, but better to apply capital M linear magnification in the equation. In that case, I told you that you want to multiply by capital V all the terms. If not, I told you want to multiply by capital U all the terms. Right? It's up to you. Since I know something about U, equals F over 2, better to multiply all the terms by U rather than V. Okay, since I have the data of object distance in terms of focal length, better to multiply all terms by U. If I multiply all terms by U, and then we can write down U over V, minus U over U must be equal to minus U over F. Simple. Then U over V means what? 1 over capital M. Linear magnification means V over U. U over V means 1 over capital M. Finally, 1 over capital M. 1 over capital M. U over U means what? Minus 1. Must be equal to minus U means what? Object distance. I know it's F over 2. F over 2 over F. F over 2 means object distance. F means focal length. F cancel out. Then 1 over capital M. 1 over capital M minus 1 if you move to the right side. Plus 1 minus half. 1 minus half going to be half. 1 over capital M. Therefore, linear magnification of the image is going to be capital M equals 2. 1 over capital M equals 1 over 2 means if it is the reciprocal, capital M going to be how much? 2 over 1. That means 2. Simple story. Question number 19 done. 20 idea. At what distance from the lens should the object be placed to obtain a real image of magnification 2 from a convex lens of the focal length 60 centimeter? At what distance from the lens should the object be placed to obtain a real image? If you want to obtain a real image, you want to keep the object beyond the focal point of the lens. Specifically, if you want to obtain a linear magnification greater than 1, that means if you want to obtain enlarged image, remember what is the meaning of an image having a linear magnification greater than 1? Just think what is the meaning of an image having linear magnification greater than 1? That image is enlarged image than the object. If you want to obtain an image having linear magnification more than 1, specifically, you want to keep the object between focal point and center of curvature. Simple logic. Very simple. If you keep the object between focal point and center of curvature only, your image will be beyond the center of curvature other side, enlarged image you will get. Simple logic. If you want to obtain an image having linear magnification equal to 2 means object must be placed in between focal point and center of curvature. Right? That idea you should have. Now they have given focal length 60 centimeter. Therefore, your object distance must be between 60 to 120 centimeter. You should find the exact value. You know that where is the object. Object must be between 60 centimeter to 120 centimeter. Specifically, what object distance you are finding that using the length equation. That is the idea. Overall, when you read the question, you should have a kind of idea, rough idea. How many of you got the answer for that question answer? Question number 20, how many of you got the answer? Question number 20, how many of you got the answer? Question number 20, how many of you got the answer? Now keep on doing, that's what I can tell. Keep on doing, that's it. Question number 20. Okay, given data focal in 60 centimeter, linear magnification given as capital 2, linear magnification given as 2, and focal in 60 centimeter. Simple idea. Question number 20. 19. Next story. 20. In question number 20, you want to understand convex lens. A focal length given as how much? Focal length 60 centimeter. Focal length is 60 centimeter. And then object must be between focal point and center of curvature. Focal point and center of curvature. That means object distance must be between 60 centimeter to 120 centimeter. Stories, I think you will understand what I mean, why I'm telling object must be between 60 centimeter to 120 centimeter, right? Optical center to focal point gap is 60 centimeter. Focal point to center of curvature gap is 60 centimeter. If not optical center to center of curvature, the gap is 120 centimeter, twice the focal length of the lens. These stories I told you many times. I hope you understand what I'm telling. When you keep an object between focal point and center of curvature, the image will be formed at the other side, inverted real enlarged image. Inverted real enlarged image beyond center of curvature. Enlarged image, capital I. This image forms beyond center of curvature, right? This idea you should have, roughly. Then sign convention, they have given the linear magnification is 2. Linear magnification given, object distance left side direction, and then the image distance right side direction. So when you apply sign convention, object distance is opposite to the direction of light, therefore positive. Image distance in the direction of light, therefore negative. Focal length, convex lens means negative. Lens equation 1 over v minus 1 over u equals 1 over f. Lens equation 1 over v minus 1 over u equals 1 over f. Sign convention negative. Sign convention negative. This one is u is positive and then v is negative. Minus 1 over v minus 1 over u equals minus 1 over f. Minus 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 cancel out. 1 over v plus 1 over u equals 1 over f. 1 over v plus 1 over u equals 1 over f. 1 over v. V is how much? I don't know. 1 over v plus 1 over u equals 1 over f. In the question, I want to find what? In the question, I want to find, they are asking us to find at what distance from the lens should the object be placed. I want to find u actually. If you want to find u, better to multiply all the terms by u. If you multiply all terms by u, multiply by u, then u over v, right? U over v plus u over u equals u over f. Simple. right? Then UOV means 1 over linear magnification, 1 over capital M. Okay, later on I'll substitute 1 over capital M means I can write down capital M as 2, right? UOV means 1 over capital M. 1 over capital M means 2. Shall I write down directly? Rather than writing 1 over capital M and again next step 1 over 2, I directly write down UOV means 1 over capital M. Therefore 1 over 2. U over U means plus 1 must be equal to, I want to find U, focal length how much? 60 centimeter, U over 60. U over 60. Then how much? 1 plus 1 over 2, 3 over 2. It's 3 over 2 must be equal to U over 60. U over 60. Then substitute. How many of you got the answer for your answer? How many of you got the answer? 180 over 290 answer. How many of you got object distance US 90 answer? 90 answer. Because I already told you that definitely object must be between focal point and center of curvature. Distance to the focal point is 60. Distance to the center of curvature is 120. Object distance must be in between 60 to 120. We got 90. We got 90. That idea. That idea we know. Right? Now what shall we do? We'll do a different story. Now I think how many of you understood how to apply Lenz equation and how to do a question that idea crystal clearance? How to apply Lenz equation and how to apply any sign convention that idea crystal clearance? That story is clear answer. The story is clear, right? Now what shall we do? Now we'll do now what will happen suppose if there are two lenses. Suppose if there are two lenses, how to do such questions? There are some important points to be remember. I will explain slowly, calmly. Now we'll talk about somewhat difficult stories. Question number 21. Question number 21. Question number 21. Question number 21. Right? 21 idea. 21. Then we'll do 22. 21, 22. Just give a try. Question number 21, 22. Question number 21, 22. 21. Then question number 22. That idea. Question number 21, they say that a convex lens and a concave lens. This time there are two lenses together. A convex lens and a concave lens are placed 10 centimeter apart. The gap between convex lens and concave lens is 10 centimeter. In the uniaxial manner, that story I will explain. The focal length of the concave lens is 10 centimeter. The parallel rays of light falling on the concave lens will be emitted from the convex lens are parallel rays after the refraction of two lenses. What is that story? I'm not clear. But they are saying that the parallel rays of light falling on the concave lens. There are two lenses. One is concave. First lens is concave. Second lens is convex. The gap between concave and convex is, if not the convex lens is 10 centimeter far from the concave lens. Initially, light rays are falling on concave lens. They are telling that a ray of light, they are telling that the parallel rays of light falling on the concave lens will be emitted from the convex lens as parallel rays after the refraction of two lenses. Find the focal length of the convex lens. Find the focal length of the convex lens. Now, this question we can do using Lenz equation manner by doing a calculation. If not, we can do the story by drawing the ray diagram. First of all, I will do the ray diagram and I will get the answer. Then I will use the Lenz equation and I will show you how to do such question. First time we are doing when there are two lenses in a question. First time we are doing a question having two lenses. First time only we are doing a question having two lenses. Give a try. Just give a try. Give a try. Give a try. Question number 21. idea. Now there are two lenses, one is concave and one is convex. Okay. Right. Here is the concave lens. And if I draw the convex lens, that is somewhere here. Okay. Right. They have given the focal length of concave lens. That is how much? Uh, focal length of concave lens is how much? 10 centimeter. Let's say F1 is 10 centimeter. F1 is 10 centimeter. 10 centimeter. They are asking us to find the focal length of convex lens. Right? I want to find F2. I want to find F2. That's my target. But what they mentioned there, they mentioned a different story. They are telling that, question number 21, the parallel rays of light falling on the concave lens. In the beginning, the light rays incident on the concave lens are parallel to the concave lens. The light rays incident on the concave lens are parallel to the concave lens. Shall we draw two light rays? You can draw any number of light rays parallel to the principal axis of the concave lens, but I will only draw two light rays. If I draw two light rays parallel to the principal axis, two light rays incident on the concave lens parallelly. If I draw two light rays, see the idea. Two light rays. Now think, you should know all the previous theory points I discussed with you. You should remember all the previous theory points I taught you. It's not difficult. Now logic, think logically, right? Think logically. Think logically, right? The gap between these two lenses, how much? The gap between these two lenses, how much? That is 10 centimeter, right? The gap between these lenses, how much? 10 centimeter. Even data. 10 centimeter. This gap is 10 centimeter. Now we know that for a concave lens, when a light ray parallel to the principal axis incident on a concave lens after the refraction seem like coming from the focal point. Am I correct? The light rays parallel to the principal axis after the refraction from a concave lens seem like coming from the focal point. Seem like coming from the focal point. Focal point is 10 centimeter from the optical center. If I draw the focal point somewhere here, focal point of concave lens is F1. The focal point of concave lens is how much? F1. What is the distance from optical center, let's say P1, optical center of concave lens P1 to the focal point of this concave lens? 10 centimeter. 10 centimeter. This gap how much? This gap how much? Very careful in this idea. This gap how much? This gap is 10 centimeter. Now I will ask you a question. Forget about this convex lens story. Only think about concave lens. Right? We know that the light rays, I told you always light rays are coming from an object. Right? What the object emits light rays, that emitted light rays are coming towards the lens. Now, in this scenario, only think about concave lens and just tell me, now there is a concave lens, light rays are parallel to the principal axis incident on the concave lens. My question is, where is the object? For the concave lens, who is the object and where it is? Raise your hand, someone if we say, for this concave lens, the object is at the infinity answer. Raise your hand, someone if we say, for the concave lens, since the light rays are parallel to the principal axis, incident on the concave lens parallelly, the object must be at the infinity answer. I explain this ideas. I explain story. I told you when the light rays are parallel to the principal axis, the object must be at the infinity. Object must be at the infinity. Without knowing previous stories, if you can't remember, you are not able to understand hereafter. Hereafter, you are not able to understand. Not only hereafter, optical instruments, eye defects, everything you are not able to understand. Right? I explained everything properly. See the idea. Remember, I told you that when the light rays incident on a lens is parallel to the principal axis, if the front of the light rays are parallel, simply if the light rays are parallel, I told you that the object must be at the infinity, right? Object must be at the infinity, right? Therefore, I draw the object is, let's say object is O1, right? Object is O1, object is at the infinity. Object is at the infinity, right? For this concave lens, where is the object? For this concave lens, the object is at the infinity. Then we know that the light rays incident on the concave lens parallel to the principal axis, after the refraction, they seem like diverging. They seem like coming from the focal point. They seem like coming from the focal point. Right? They seem like coming from the focal point. Right? They seem like coming from the focal point. Right, me? All good, me? Then for this concave lens, where is the image? Forget about the convex lens story. You can learn something new concepts from this question. For the concave lens, no doubt that object is at the infinity. No doubt. Right? After the refraction, we understand that these two light rays seem like converging exactly at the focal point of this concave lens. Then my question is, where is the image? What is the image for this concave lens? For this concave lens, the image is formed exactly at the focal point. Right? The idea is very simple. This concave lens takes the object at the infinity, creates an image exactly at its focal point. For the concave lens, the image is exactly here. For the concave lens, the image is exactly here. Right? Red color pen, I draw that image as I1. Image as I1. I1. Raise your hand, someone if you understood that. For that concave lens, object is at the infinity. That concave lens creates an image exactly at its focal point. That is the image for the concave lens. Object for the concave lens is at the infinity. Image of that concave lens is at the focal point. That idea clear answer. That idea clear answer. That idea clear. Right? That idea clear. Now hereafter what's happening, right? Now forget about this concave lens. Now forget about the concave lens. Now think about you are the convex lens. Think about you are the convex lens. Right? Now you don't know what's happening before what's happening, we don't know. Right? Now there is a window. Roughly I'm telling. Roughly for you to understand the idea, roughly I'm telling there's a window. Right? You are getting the light rays through your window. Right? You are getting a light rays through the window. We don't know what's happening beyond the window. We don't know what's happening. Right? We don't know what's happening beyond the window. We do the assumptions. We come to the conclusions based on the light rays coming after the window. Right? Same idea, same idea. Just think you are the convex lens. You are the convex lens. You don't know that there was a concave lens here. Oh, you don't know light rays initially incident on the concave lens. You don't know. You don't know that before these light rays incident on the convex lens, before the light rays reaching on you, you don't know whether the light rays already reached on someone else, whether the light rays already incident on someone else, and whether those light rays already undergone refraction or anything. You don't know, right? You don't know anything about that. You don't know actually what happened to the light rays actually. You come to a conclusion, you come to a judgment based on the direction of light rays incident on you. Now, what you understand? If you are the convex lens, you see like these two light rays incident on you. If you are the convex lens, you think like this, right, there are two light rays incident on me. These two incident light rays are coming in these directions. These two light rays are incident on you through this direction and this direction. Okay. So you are coming to a conclusion that that means since these two light rays, I am the convex lens, I am the person. Since these two light rays coming to me in this direction, if I extend these two light rays backward, who must be there? Now I am coming to a conclusion. Very simple story. Listen very carefully. I'm expecting replies from everyone. If your answer can be right or wrong, it's completely all right. To check whether you got the idea or not, I'm expecting your response. Okay, right? Now you are the convex lens. I told you in the beginning. In the beginning, when I start the lesson, I told you that objects emit light rays. Objects emit light rays. The light rays emitted by the object raise the convex lens, so concave lens. Okay, right? Suppose just think you are the convex lens. You come to a conclusion about location of the object based on the direction of light rays incident on you, because you are not able to see what happened to the light rays before, right? What you can come to a conclusion is based on the direction of light rays incident on you only, you are able to decide the location of the object, right? Okay. So then you notice that, okay, there are two light rays incident on me. There were two light rays incident on me. Now you want to check. Now you know that no doubt, you know those two light rays should have come from an object. You think like that. Okay. Now you are sleeping, right? Suddenly you notice that two light rays incident on you. Then you came to a conclusion. These two light rays should definitely have come from an object. Then how do you track the object? How do you track the object? Right? Your eye. Is your eye. Some stories, okay? Is your eye. Now there is a candle. Okay? So you can't see the candle. Just think that candle is really far from this eye. Just think like that. Now you were sleeping. You are sleeping, right? Two light rays. Two light rays. If I do two light rays emitting from the candle, you realize that there are two light rays incident on me, right? There are two light rays incident on me. You know that there's a candle. You know there's a candle. You know there's an object, because we know in order to incident light rays on me, there must be a light emitting source. There must be an object simply. In order to emit two light rays on me, there must be an object. Okay. So you know these two light rays are emitted by an object. How do you track the location of the object? How do you track the location of the object? Simply, you track the path of the light ray and you go behind. If you track the path of the light ray and if you go behind, If you track the path of the light train, if you go behind, like these two light rays are converging, right. Exactly. The object is candle. Here is the object. Same thing. Same thing, understand? For this convex lens, realized there are two incident rays incident on the convex lens. Convex lens definitely realized that these two light rays have come from an object. The way how convex lens thinks. Convex lens thinks that right, these two light rays have come from an object. Now convex lens wants to locate the location of that object. So how, what is the only way to decide? What is the only way to track the location of the object? We have to go. We have to track the path of this incident to light rays and we want to go behind. We should track the path of these two incident rays and we have to go behind. If you go behind, convex lens thinks that who has the object? Convex lens thinks that. Now when you track these two path of the light rays and when you go behind, convex lens decides that this is the object for the convex lens. But the actual object is at the infinity. For this concave lens, actual object is at the infinity. The image produced by the concave lens is exactly here. But convex lens doesn't know those scenarios and everything. What convex lens does is, there are two light rays incident on the convex lens. When this convex lens tracks the path of these two light rays backward direction in order to find the location of the object, convex lens decides that. Convex lens decides that the object is somewhere here. But actually, that is the image formed by the concave lens. But convex lens decided that object of that object is here. Right? Do you understand? So convex lens thinks that object is somewhere here. Raise your hand, someone if you understand the object for this convex lens is this image I1 and some. Raise your hand, someone if you say the object for this convex lens is the image this one and some. That is the first idea. All right, thereafter simple story. All right, you want to understand the image for this concave lens going to be the object for the convex lens. The image for this concave lens is going to be the object for this convex lens. That is a difficult idea. Many people don't understand. If I tell that, the image for the concave lens is the object for the convex lens, many don't understand. Many will confuse. Right? I hope that I have explained up to a good level. I hope everyone understood. Rightly simple. Then this image is the object for this convex lens. Object is, let's mark it as O2. Object for the convex lens is, I mark same this one as O2. O2. Object O2. Second object. First object is O1. For the concave lens, object is O1. That is at the infinity. For the concave lens, image is I1. That is at the focal point of concave lens. For the convex lens, object is O2. That is the image formed by the concave lens. Now what will happen? This is the object. Two light rays are incident on the convex lens. After the refraction from these two light rays from the lens, there will be an image. There will be an image. Right? Now what is the object distance? When you consider convex lens, what is the object distance? Reply everyone. Reply everyone. Now they mentioned clearly in the question, they mentioned that after refraction from these two lenses, the light rays refract parallel to the convex lens. The light rays refract parallel to the convex lens. The light rays refract parallel to the convex lens. Parallel to the convex lens. Okay, right? When you consider convex lens, When you consider convex lens, what is the object distance? Reply everyone. Reply everyone. If you consider convex lens, what is the object distance? Reply everyone. Give some replies. Reply everyone. When you consider the convex lens, you know this is the object. Object is exactly here. What is the object distance u? Reply everyone. Reply everyone. I'm expecting a response from everyone. Reply everyone. I need a value. When you consider this convex lens, what is the object distance? Reply everyone. Reply everyone. Give a try. Everyone give a try. Everyone give a try. 20 centimeter. Right, it's 20 centimeter. Ne? Very good. It's 20 centimeter. Right? Ne? Okay. Now, after refraction, they mentioned that light rays are parallel. It's obviously, right? They mentioned, okay, they mentioned then object is here. The light rays are coming from the object. Object distance 20 centimeter. After refraction, they mentioned light rays are parallel. So just tell me that what should be the focal length for this convex lens? Now, you know, for this convex lens, object distance is 20 centimeter. For the convex lens, object distance, let's take it as u2, it's 20 centimeter. That is how much? That is how much? This is going to be, u2 is going to be how much? 20 centimeter. 20 centimeter. My question is, after diffraction, these two light rays became parallel to the principal axis. What should be the focal length of this convex lens? What should be the focal length of this convex lens? Reply everyone. Standard light rays. Standard light rays. If you can remember the idea, you can read the answer. Reply everyone. What should be the focal length of that convex lens? Reply everyone. Reply everyone. It must be exactly 20 centimeter. You know why? I told you one story. When I was explaining standard light rays for a convex and concave lens, I told you that, right? If there is a convex lens, right? The light ray passing through the focal point. I told you the light ray passing through the focal point after refraction become parallel to the principal axis. The light ray passing through the focal point after the refraction from a convex lens becomes parallel to the principal axis. Okay, convex lens. After the refraction parallel, you can think opposite. You can think opposite idea. You can think opposite way also. The light ray parallel to the principal axis after refraction passes through the focal point. Right? Then in order to refract parallelly, this light ray should have come from the focal point. In order to refract parallelly, these two light rays should have come from the focal point of convex lens. Then remember, focal point of this convex lens is also exactly at the same location. I don't know how many of you understand, right? Very simple logic. In order to refract parallelly from a convex lens, that light ray should have come from the focal point of the convex lens. This light ray should have come from the focal point of the convex lens. Therefore, you want to understand this light ray is coming from the focal point of this convex lens. Therefore, remember, here is the focal point. The distance to the focal point is how much? 10 plus 10, 20 centimeter. Therefore, focal length is how much? 20 centimeter. Right? How many of you understood focal length F2? Focal length of the convex lens is 20 centimeter answer. Focal length of convex lens is 20 centimeter answer. How many of you understand? That idea clear answer genuinely? That idea clear answer genuinely? If you have doubts, you can ask that. It's up to you. It's up to you, right, me? Okay. Then, sir, I have a problem. Okay, now, sir, now you explained for this concave lens. For the concave lens, you explained that object is at the infinity. The reason is since the light rays are parallel incident on the concave lens, you told us that the object is at the infinity. Object for this concave lens is this object O1 at the infinity. Image for this concave lens is this I1 at the focal point of concave lens. Then you explain that for this convex lens, object is going to be this one. Where will be the image? Where will be the image thing? Where will be the image? Reply everyone. Now we are observing. You are looking at this. Now you are looking from this side. Thing like that. You are looking from this side. This is your eye. This is your eye. I'm asking that for this convex lens, object is at this point O2. Where will be the image for this convex lens? What is the image of this object O2 after diffraction from a convex lens? Anyone? Any answer? Reply everyone. I will show you using Lindsay equation also properly. Reply everyone. Just give some replies. Just give some replies. Just give some replies. For this convex lens object is here. Where would be the image of this convex lens? I mean, this one's image is where? Anyone? Any idea? Where is? At the infinity. Why? Just extend these two parallel light rays backwards. Right? After refraction from this, see the idea, after these two light rays refract from this convex lens, they are parallel, right? They are parallel. If you extend the light rays backward direction in all, because these two light rays never converge in the right side. This is the refracted rays. If you want to decide the location of the image, you should check whether these two refracted rays are converging somewhere at the right side. We know that since these light rays are parallel, they will never converge at the right side. In that case, if you realize light rays are never converging right side, I told you that you want to extend these light rays backwards. So when you extend these light rays backward also, you know that they will never converge. Therefore, I told you that in that case, image will form at the infinity. Then I told you that image will be formed at the infinity. If from what shall we do? This idea really hangs up. First idea, okay. First idea, okay. What you want? If just check with the you understood these stories. First story is for the concave lens object is at the infinity. Why object is at the infinity for this concave lens? That idea. After the refraction from the concave lens, why image is formed at this point? Why this is the object for the convex lens? Why light rays has to be parallel? And why the image of this convex lens is at the infinity? Those points are very clear and sound. Those points are genuinely very clear. Raise your hands. Raise your hands. Very clear and sound. Very clear and sound. Very clear and sound. Right. I think many, I don't know why not raising any doubt you can ask. You are not talking. You are not asking the doubts also. What is the problem? I don't know. Last days, don't do that. Okay. If you can ask few questions once again, sometimes not from the beginning till the end. If you can ask some questions at least once again to give some clarity, some small ideas once again to make all of you understand. But I am assuming that all you understood and I am doing thereafter, right? That's the idea. Okay. Now what you do, first of all, we'll do an explanation. Okay, we'll do an explanation. First, draw this diagram. Okay, you should draw this diagram obviously. right? After drawing this diagram, once again, only draw the concave lens, parallel light rays, entity seem like coming from focal point. Stop from here. Again draw this part, stop from here. Don't draw this one or anything else. Quickly. Finish drawing, we'll write a small point and then we'll go one by one. We'll take a break. Hands up, who want to take a break? Hands up. Okay, first we'll complete the story and we'll take a break. We'll complete the story and we'll take the break. Okay, we'll complete the story, we'll take the break. Quickly. Quickly. Idea is very simple. Remember, hereafter, the image produced by one lens going to be other lens object. That is the idea. Keep in your mind that the image produced by first lens going to be the object for the second lens. Keep in your mind. The image produced by the first lens going to be the object for the second lens. That is the idea. Right? Finish drawing, hands up. If you finish drawing, raise your hands. Don't raise down. I hope that you guys do this diagram again. Only this part. Only object is at the infinity. O1, I1, parallel light rays coming from F1 focal point. Till here. Write down. Since light rays incident on concave lens parallelly. Since light rays incident in a notebook, okay, notebook. Since light rays incident on concave lens parallelly. Since light rays incident on concave lens parallelly, the object for the concave lens must be. The object for the concave lens must be at the infinity. The object for the concave lens must be at the infinity. Right? At the infinity. Full stop. Next point, write down. Next point, the same story, next point. After the refraction from concave lens, after refraction from concave lens, those light rays, those refracted light rays seem like coming from the focal point of concave lens. Those refracted light rays seem like coming from the focal point of the concave lens. Seem like coming from the focal point of the concave lens. Therefore, a virtual image is formed. Sorry, therefore, image for the concave lens is virtual image. Therefore, the image for the concave lens is virtual image formed at that focal point. Therefore, the image for the concave lens is therefore, the image for the concave lens is an virtual image formed at the focal point. Formed at the focal point. Formed at the focal point. Okay, right? Okay, that story okay. Now what you do again, Don't draw the concave lens. Don't draw this parallel light rays. You draw dotted light rays, then dark two light ray incident on this convex lens become parallel. Right? Dotted light rays, dark light rays, a convex lens parallel. That story. Distance 20 centimeter. That diagram draw it. That diagram draw it. That diagram draw it. I will explain this idea using Lenz equation also. That diagram draw it. That diagram draw it. Finish drawing, answer. Once you finish drawing, raise your hands. Once you finish drawing, raise your hands. These days, if you have doubts, ask your doubts and all. Don't keep any doubts hereafter. Okay, ask your doubts and clarify everything properly. Don't keep any doubts. Right? Finish drawing the diagram, raise your hands. Finish drawing, raise your hands. Finish drawing. Finish drawing, raise your hands. Quickly. 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 Once you finish drawing, raise your hands. So this story you will understand when we do lots of questions. You will understand the idea. Don't worry. We'll do lots of questions. We'll do. We'll do lots of questions. Don't worry. Okay. Write on there. Write on there. Write down there. Since light rays incident on the convex lens, since light rays incident on the convex lens, since light rays incident on the convex lens seem like coming from the seem like coming from the seem like coming from the since light rays incident on the convex lens seem like coming from the focal point of the concave lens, seem like coming from the focal point of the concave lens, focal point of the concave lens, comma, comma, focal point of the concave lens, comma, convex lens decide that, convex lens decides that the object for the convex lens is, convex lens decides that the object for the convex lens is at that point. The convex lens decides that object for the convex lens is at that point. Okay, that's the idea. Next point. Since it is mentioned that light rays are parallel after the refraction from the convex lens. Since it is mentioned that light rays are parallel after the refraction from convex lens. Since it is mentioned that light rays are parallel after the refraction from the convex lens, light rays are parallel after refraction from the convex lens, comma, the light rays incident on the convex lens, the light rays incident on the convex lens should have come from the focal point of convex lens. The light rays incident on the convex lens should have come from the focal point of the convex lens. Therefore, object for the convex lens, comma, focal point of concave lens, comma, therefore, object for the convex lens, comma, focal point of concave lens, comma, focal point of convex lens are at the same point. Therefore, object for the convex lens, comma, focal point for the concave lens, comma, focal point of the convex lens are at the same location. Right? So F1, focal point of concave lens also at here. Focal point of convex lens also should be at same point. F2 also somewhere here. F1 also the same point. F2 also the same point. Once again, summary simple. Before the break, we'll do a summary. Very simple. There are two lenses. First of all, you want to consider refraction of one lens, even though there are many lenses. Forget about the other lenses. First, you consider the lens where light rays incident first. Out of these lenses, very clear that light rays incident first on this concave lens. Right? The light rays incident first on this concave lens. Then object is at the infinity y. Object for the concave lens. Okay, object for the concave lens is at the infinity y. Light rays are parallel to the concave lens. Then it creates an image exactly at the focal point of the concave lens. Image is at the focal point, object is at the infinity. For this convex lens, object is at that image for the concave lens. Image of the concave lens is the object for the convex lens. Right? Then image of this convex lens is at the infinity. That is the idea. Right? What shall we do? We'll take a small break and come. Time is, I think, 8:53. Time is 8:55, 19. Come at 19. We are doing the class till 10:15, 10:30. After the break, what shall I do? Once again, I will show this idea using lens equation. Then I will talk you about compound lens, how to find the focal length and how to find compound lens power story. Then also I will do few more questions. But anyways, this Sunday I will do definitely optical instruments. Night time we will put some sessions if it is possible. Tomorrow night, maybe Thursday night, 10 p.m. onwards. Then Friday night, 10 p.m. onwards, we'll do few more extra sessions and we'll do questions. Not theory. We'll do lenses tube questions. Okay, we'll do in that way, right? Just come at 9, 10. Come at 9:10. Take your break and come at 9:10. Just reply whether all good. Just give me a small reply whether you all can hear me speaking. Give a small reply. All good, ne? Right, okay. Now this idea. Now, if I tell that when the object is at the infinity and the image for the concurrence is at the focal point, and for the convex lens object is at here, then the image will be at the infinity. That idea, what shall I do? I will apply lens equation and I will show you. Okay. So once again, I will show you how to apply lens equation and how to get these ideas. Once again, I will show you. Right, this question I will take time, I will explain. Right, tomorrow and day after tomorrow also we'll do some night sessions to do the remaining two questions. Okay, Sunday we'll start the optical instruments. Okay. Now see the idea now. Now definitely what is your level doesn't matter. That if they mention that light rays incident on the concurrence is parallel to the concave lens, you want to understand. You want to understand the light rays are parallelly incident on the concave lens. You want to understand. No doubt, object must be at the infinity. There is no logic behind that. Then what is the object distance if you consider concave lens, right? For the concave lens. For the concave lens, object must be at the infinity, right? Object must be at the infinity. Then what is the object distance? If you measure the object distance, that is the infinity. If you measure the object distance, that is going to be equal to how much? Infinity. Very large number, very large value, right? And just think that you don't know where will be the image. Now I explained that when the light rays are incident parallelly to the concave lens, I told you that image will be formed exactly at the focal point of concurrence. Just think you have no idea about that, forget about that, you don't know where will be the image, right? So you have no idea where will be the image of this object, right? You have no idea. And just think you don't know whether the image will be formed at the left side of the concave lens, so image will be formed at the right side of the concave lens. That is also you don't know. We have no idea about image distance. I don't know anything about image distance. I don't know. Right? But they have given the focal length of the concave lens is how much? 10 centimeter. Focal length of the concave lens given as 10 centimeter. Already data you know, object distance infinity, focal length of the concave lens how much? That is 10 centimeter. In order to find the image distance, you can use lens equation. Apply lens equation. Lens equation you can apply 1 over v minus 1 over u equals 1 over f. Right? 1 over v minus 1 over u equals 1 over f. Apply lens equation. Done. Right. Then apply sign convention. Sir, now it's a concave lens, therefore focal length sign is positive. Since the object distance, anyhow, we know that direction of light is right side. Light rays are incident on the concave lens to the right side direction. Light rays are moving right side direction. Direction of light is right side direction. Object distance infinity. Direction of object distance left side. Direction of light is right side. Therefore, object distance opposite to the direction of light. Therefore, U is positive. So when it comes to image distance, I have no idea where is the image. It's completely all right. If you have no idea about the location of the image, don't put any sign for the image. My target is find the image distance. Don't you put any sign for the image. It's okay. Then substitute the remaining values. My target, if you don't substitute any sign for the image, you will get the image distance with the sign. If you don't apply any sign to the image, distance, you will get the final answer for the image distance with the sign. So 1 over V, I want to find V actually, right? Minus object distance infinity. 1 over infinity must be equal to focal length how much? 1 over t plus 1 over t. You know that 1 over infinity means how much? If you divide any number by infinity, remember it is 0. If you divide any number by infinity, it is 0. Therefore, 1 over infinity means how much? 0. 1 over infinity means how much? 1 over infinity means how much? 0. Therefore, I can write down 1 over v equals 1 over t. 1 over v equals 1 over t. 1 over t. So finally, when you subject the image distance, you are getting the answer as v equals how much? V equals 10 centimeter. What is the sign for the image distance? Positively, just 10 centimeter means plus 10 centimeter. Plus 10 centimeter. Very clear that, sir. Already I told you, without using the Lenz equation, you can come to a conclusion. When the light rays are parallel to the principal axis, parallelly incident on the concave lens, definitely image will form at the focal point of the concave lens. I applied Lenz equation and I came to a conclusion. The image distance must be 10 centimeter, which is exactly equal to focal length, right? Sign is positive. What is the meaning of positive? I told you that. Positive image distance means image distance is in the image distance is in the opposite direction of light. Right? If you get the sign for the distance as positive means what? Image distance must be opposite to the direction of light. Direction of light is right side direction. Direction of light is right side direction. That means image distance must be opposite to the direction of light. Therefore, we know that image must be at the left side. Therefore, image must be at the left side. Right? Then we know that image must be at the left side. Okay. Therefore, I mark that object as O1. Object is O1. The corresponding image is at the left side of this concave lens. Image is how much? I1. Virtual image. It's a virtual image. Image going to be how much? I1. Right? I1. Somewhere here I1 image. Okay. Now this virtual image going to be the object for the convex lens. That's clear. This virtual image going to be the object for the convex lens. This gap is how much? This gap 10 centimeter. This gap is 10 centimeter. Right? Now if I do that story, I will take time and I will explain this idea. Thereafter, I don't take this much of time to explain a question. Right? And now for this convex lens, I told you, this image going to be the object for the convex lens. Simply remember, always first lens image going to be second lens object. Always first lens image going to be second lens object. Keep in your mind that idea. Right? Okay. Now if I draw the convex lens, next story. Okay. Then finished. If I draw the convex lens, I don't know the focal length of convex lens. I don't know. Actually, we want to find that only. Right? Okay. And okay. Right. Then they mentioned that here object is where? For the convex lens, I1 is the object. I take it as O2. I1 is the object. That is the O2. Object distance how much? I1 to convex lens distance how much? 20 centimeter. Object distance how much? Left side direction. U is how much? U2 actually. 20 centimeter. 20 centimeter. Object distance 20 centimeter. Focal length of the convex lens I don't know. The image will be formed at what? Where? The image will form at the infinity. The image will form at the infinity. Because light rays are parallel means you want to understand After refraction from the lens, light rays are parallel, means remember the image must form at the infinity, right? The image will be formed at infinity somewhere here, right? I draw the image as I2 somewhere here. The object is O2 somewhere here. Let's take it as here O2. Object is O2. The respective image will be I2, that is at the infinity. The image will be I2, that is at the infinity. So what is your V? Image distance, that is infinity. Apply lens equation. If you apply lens equation, 1 over V minus 1 over U equals 1 over F. 1 over V minus 1 over U equals 1 over F. Sign convention. Right, sign convention, focal length I want to find, the convention sign is minus, direction of light is right side direction, but object distance left side, image distance also left side, therefore you can put plus plus. Image distance how much? 1 over infinity, minus object distance how much? 1 over 20, focal length how much? Focal length minus, I don't know, I want to find F only. 1 over infinity means 0. Minus 1 over 20 equals minus 1 over F. Minus minus cancel out. Then you know that 1 over 20 means 1 over F. F means how much? 20. Simple. This 0 minus 1 over 20 must be equal to minus 1 over F. When you substitute F, that's going to be how much? Just 20 centimeter. So simple story. I know that sometimes many of you feel like very complex because it's the first question that you are dealing with. That might make you uncomfortable and very complex, this question, but don't worry. When we do lots of questions, you will get the idea, right? Till now, all the ideas crystal clear and till now, everything I taught you till now, everything is very clear and very clear. Very clearly, that is okay. Now, one last theory part, then story finished. One last theory part. Just put your topic in your notebook. If not, I have given some space in the tutor also. Put your topic. Put your topic. Then last theory, then finished. Give me a second. Right. Okay. Give me a second. Okay. Right. Put your topic compound lenses. Put your topic compound lenses. Put your topic compound lenses. I will do lots of questions. Don't worry. Compound lenses. Write down. A compound lens is obtained. A compound lens is obtained. A compound lens is obtained by joining, by connecting, by joining two or more than two lenses together. A compound lens is obtained by joining, by combining, if not by connecting two or more than two lenses together. Two or more than two lenses together. Right? This idea is not difficult. Last theory point, then lenses, all the theories are done. I took time and explained everything. See the idea. Okay. See the idea. Now compound lenses. Compound lenses. Now you can connect, you can bring many lenses together, but to explain this idea, I take two lenses. Now we can connect, there are two convex lenses together. We can connect, we can join two convex lenses having different focal lengths or having same focal length together. If not, we can connect two concave lenses together to form a new lens. If not, one can combine a convex lens and concave lens together. In that cases, how are we going to find the power of that? If not, focal length of that combined lens system. That's our target. Okay, right? Remember, uh, remember this idea very simple. Okay, now one can combine two convex lenses together. This convex lens having a focal length, let's say f1, and this convex lens having a focal length f2. So once I bring them together, once I connect them together, how do we find the focal length of combined system? If not, one can connect one convex lens and one concave lens. One can consider two concave lenses, three concave lenses, four concave lenses. How to find the focal length of combined system? That's our target. The equation is very simple equation. Just consider now focal length of the combined lens system is simple if. Focal length of the combined lens system is simple if. Remember, the focal length of 1 over simple if, 1 over focal length of combined lens system equals 1 over f1 plus 1 over f2 plus 1 over f3. Likewise, a number of f1, f2, f3 means the focal length of each lens. If there are simple number of lenses, 1 over focal length of first lens plus 1 over focal length of second lens plus 1 over focal length of third lens plus something. After writing this equation, you want to apply the sign convention, right? After this equation, you want to apply the sign convention, okay? You should apply the sign convention, right? Suppose if the f1 is focal length of a convex lens, the sign is negative. Suppose f2 means focal length of a concave lens, sign is positive. That is the idea. That is the idea. If you want to find the power of the compound lens system, the power of the, let's say, capital P is the power of the compound lens system. That is equal to P1 plus P2 plus P3 plus likewise Pn. If there are simple number of lenses, when you combine together, when you add all the lens powers together, P1 plus P2 plus P3 plus likewise Pn, that is going to be the power of the combined lens system. In that case also, you want to apply sign convention, but different story. I told you, when you are finding the power, for a convex lens, power is positive. For a concave lens, power is negative. When you are finding the focal length, I told you that for a convex lens, focal length negative. For a concave lens, focal length positive. That's what you want to remember. Okay, that is the last theory. Write down like this. Write down. Just write down. First of all, this diagram: F1, F2, F1, F2, F1, F2. Okay. Now we all know that before writing the stories, I will tell you. First of all, draw this diagram. We know when you connect two convex lenses together, the compound lens also must be a convex lens. Right? When you connect two convex lenses having focal length f1, f2 together, the compound lens must be also a kind of convex lens having a focal length simple if. When you connect two concave lenses together, definitely that compound lens also must be a kind of concave lens having a focal length f. But the problem is when you connect a convex and concave lens based on the magnitudes of f1, f2 values, the compound lens can be a convex lens, so the compound lens can be a concave lens. That depends. That depends. That depends. This diagram draw it. This diagram draw it. This diagram draw it. 9:30. Okay. Write down. Write down. If the focal length of compound lens system is, okay, sorry. If the focal length of, write down, if the focal length of compound lens, if the focal length of compound lens if the focal length of compound lens is simple left, if the focal length of compound lens is simple left, when simple in number of lenses connected together, when simple in number of lenses connected together, comma then, write in this equation 1 over f, 1 over f1 plus 1 over f2 plus 1 over f3 plus plus last one is 1 over f1, 1 over f 1 over f 1 over f 1 over f right? Write on below red color pen. Red color pen. After applying the above equation, sign convention must be applied. After applying above equation, sign convention must be applied. Sign convention must be applied. Right? Simple story. Next point, write on next point. If the power of a compound lens is capital P, if the power of a compound lens is capital P, if the power of a compound lens is capital P, if the power of a compound lens is capital P, if the power of a compound lens is capital P, comma, for simple in number of lenses, for simple in number of lenses, then for simple in number of lenses, then capital P equals P1 plus P2 plus P3 plus something 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 plus Pn. Okay. Right on next point. After applying above equation, sign convention must be applied. Right? But remember, when you are considering power, for a convex lens sign is positive, for a concave lens sign is negative. Huh? Remember the story. That's the end of the theories. That is the end of all the theories in lenses. I think I have done everything properly. Okay. I think I have done everything properly. Right. Okay. Time is 9:35. We'll do hereafter questions. Right. Theory wise, everything is very clear and some. Lenses, theory wise, everything is very clear and some. Theory wise, everything is very clear and some. Right. Okay. Have doubts, ask. If you have doubts, ask. Right. That's what I can tell. That's what I can say. Rather than separately asking via WhatsApp at this moment, if you ask you, I can see the chat now. Right. Then I can give some ideas. Not all the questions maybe. At least few I can respond. It's up to you. Right. Okay. Now we'll do the questions more. Good, dude. Theory wise finished. Questions. Okay. Okay. Question number 25. Now 25 story, somewhat different stories. Question number 25. Give a try. Question number 25. When an object is placed 12 centimeter in front of a convex lens, when an object is placed 12 centimeter in front of a convex lens, a virtual image is obtained. Virtual image is obtained. Right? That means object is exactly in between optical center and focal point. Then only there will be a virtual image formed behind the object, the same site, right? Okay. When the object was moved 8 centimeter further from the lens, a real image of same size as the first image was obtained. Find the focal length of the lens. Find the focal length of the lens. Find the answer. 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 Get the answer. Question number 25. Question number 25. Right me. You are right. Object distance how much? When an object is placed 12 centimeter in front of a convex lens. Virtual image is formed when the object was moved 8 centimeter further from the lens. Real image of the same size as the first image was obtained. Get the answer. Get the answer. Always draw a sketch and mark the location of the object and image. Then you will get a good understanding, good idea. Okay, right. Okay. Okay, right. So when the lens is here, convex lens, okay, right. Do we know the focal length of convex lens? I think we don't know. I think we don't know. We want to find the focal length only. I want to find the focal length only. Object distance 12 centimeter. Object distance 12 centimeter. Right. Then definitely we know that object O. Definitely we know that object distance how much? 12 centimeter. Right. U1, object distance U1, that is how much? 12 centimeter. When U1 is 12 centimeter, images, definitely in order to form a virtual image for a convex lens, definitely object must be between optical center and focal point. Definitely object must be between optical center and focal point, right? Okay, the respective image I will draw behind the object at the same side. Respective image will be somewhere here or here, whatever. It is the image. Okay. You can't see it, but draw a large image. Draw a large image. Draw a large image. Okay. Draw a large image. Draw a large image. Okay. This image is going to be, I mark it as I1. I1. Object height is, we can take it as H naught. If you want to mark the image height, I can mark it as H1. H1, right. What they mentioned that when the object was moved 8 centimeter further from the lens. Object was moved 8 centimeter further from the lens. Right? That means I am moving the object away from the lens 8 centimeter. If I move the object away from the lens 8 centimeter, what is the now object distance? 12 plus 8, 20 centimeter. Now my object distance how much? 20 centimeter. 20 centimeter. Right? Right now my object distance how much? Now my object distance how much? 20 centimeter. 20 centimeter. right? 20 centimeter. Same object, same size object, right? Object is here, same size object. Then the corresponding image is going to be, right? Then if you move the object again, you will get a real image. Am I correct? When the object is in between optical center and focal point only, you will get a virtual image. If you move the object away from the lens by 8 centimeter, same size, real image is formed. Right? That means now object is away from the focal point. Object is away from the focal point. Right? I think still it is in between focal point and center of curvature. You know why? I will tell you. Anyone will agree that now the object definitely must away from the focal point. Now everyone agree object must be away from the focal point. But if I tell object is exactly between F and C now scenario, sometimes you have a doubt. How do you exactly tell? We are very clear. Object must be away from the focal point. Then only a real image will be formed at the right side. But how do we tell object must be between focal point and center of curvature? I will tell you the reason bit later. Now object distance how much? U2 is 20 centimeter. Now your object distance U2 is how much? 20 centimeter. U2 is how much? 20 centimeter. 20 centimeter. Right? 20 centimeter. Then the image will be formed at the right side. It's a real image. Right side, enlarged image. Why I am telling the image must be enlarged? Because they mentioned definitely in when the object is between optical center and focal point, the image must be an enlarged image. That virtual image must be an enlarged image. They told the question, right? This scenario and this scenario, images are in same size. Images are in same size means this image must be larger than object. Am I correct? If the before scenario and now scenario, they mentioned image size are same. Same image size means this image also kind of enlarged image than the object. In order to have an enlarged image, object must be between focal point and center of curvature. That idea you should have, right? That idea you should have. Okay. Then this image size also I can mark it as H2 if not H1. H2 if not H1, okay? H2, and this is H2 is equal to H1, whatever. Okay, right. Then okay, then is the given data. Given data. Now what we can do? Now they are asking us to find the focal length. Right? What you can do, you can involve linear magnifications. Right? You can involve linear magnifications. Give a try. Linear magnifications, give a try. Right? There are different ways to get the answer. Now different people can go with different methods and they can get the answer. You don't follow my method is not the only method to get the answer. Right? There are different ways to get the answer. Give a try. Our target is finding focal length. That's our target. Same lens. Our target is find the focal length. Give a try. Okay. So what we know is since both the scenarios image height is same, both the scenarios height of the image is same object. So what we know, linear magnification, we know that linear magnification means we all know that image height over object height. If not, image distance over object distance. In this scenario, we know that this scenario also image height h1 over object height h0. This scenario also image height is h1 over object is h0. Both the scenarios have same linear magnification. Nice story, ni? Both scenarios have same linear magnification. Now think the way I think. You don't want to follow my way. Now the way how I thought. Now I thought that first of all I drew a sketch and I marked the given data. Then I thought, right, okay, now first scenario and second scenario, image are in same size, object is same object, therefore Linear magnification in first scenario and linear magnification second scenario same linear magnification, capital M, right? I want to find if. I don't know if. Linear magnification also I don't know, but both of them have same linear magnification. Normally they give two cases. Normally they give two cases to get two equations or many equations, right? I know that we can't directly apply Lenz equation for one scenario and we can't get the answer, right? Sometimes I may have to apply Lenz equation for this scenario, both. I want to apply Lenz equation for this scenario and this scenario, both. I don't know. I'm thinking, right? So what I noticed, linear magnification same for both of them. And I know object distance u. I know you. This scenario I know you. This scenario also I know you. So I'm thinking better when I definitely we have to apply Lenz equation. Any Lenz question we have to apply Lenz equation. I'm thinking better when I apply Lenz equation, better to involve linear magnification in the equation. Better to keep u. Better to keep f. Why? Because f is what we want to find. Right. Now what I thought is I want to apply Lenz equation for both the scenarios, but in the Lenz equation I want to modify, and Lenz equation must only include capital M, U and F. Now okay, now I can give a try. Still I don't know if I get the answer or I don't know, but I'm giving a try. I don't know whether I get the answer or not. These are difficult questions. Normally you are level exam, they don't ask this level, right? A compound microscope story, if you really understood, only compound microscope story only, there are two Lenz stories there. If you understand compound microscope idea and eye defect idea, now they don't go this deep and they don't ask question. But doing these questions make your normal AL syllabus easy. That is the idea. That is the idea, right? Okay, if you understand these ideas means definitely compound microscope story, optical instrument stories, ID fixed stories, definitely will understand. Okay. Hereafter, upcoming lessons are two Lenz story. And then one's images, others object. First one's images, others object. That idea is there. If you don't understand, can't. So when you do lots of questions, you will get a kind of clarity and you will understand more. If I, rather than doing one question, if I do some difficult questions, many, if you're really focusing properly, if you're really focusing, it's up to you. Now it's up to you. If you can focus properly, yes, you will understand. More and more questions we do, more and more you ask doubts, you ask questions from yourself. Why sir did that way that question? This way is do it is in this way, right? You can learn, you will get lots of questions, then you will understand and you will definitely will understand. Okay, right. How many of you understood what I'm going to do? I'm going to apply Lenz equation for both of them. I'm going to involve capital M, linear magnification into the equation. Since they have given object distance as given data, I thought of involving U and focal length obviously because I want to find definitely F must be in the equation. How many of you understood that idea? Involving modifying the Lenz equation in terms of capital M, U and F idea and sum. Idea, right? Okay. Now Lenz equation. Now Lenz equation for this scenario, right? Case number one. This is case number one. Case number one. Case number two. Case number one Lenz equation. Okay, case number one Lenz equation. Right? Case number one Lenz equation. 1 over V, 1 over U, 1 over F. Sign convention. For case number one, sign convention. Convex means negative. Negative. Object distance opposite to the direction of light. Direction of light is right side direction. Object distance left side direction. Therefore, positive. Image distance also. Image also left side. Image distance V. V1 something. V1 something. Right. Direction of image distance is opposite to the direction of light. Therefore, V also positive. I thought of multiplying in order to involve capital M into the equation. I thought of multiplying all terms by U. If I multiply everyone by u, I can get the idea. I can get the idea here u over v. U over v means, now, okay, I can follow all the steps, but you want to understand me. Here u over v means what? U over v means 1 over capital M. Ni. Right? Therefore, you understand. Yeah, I can write that step u over v minus u over u minus u over f. But now, I don't want to do that step, ni, because we know ni, u over v means what? 1 over capital M. 1 over capital M. I'm involving the 1 over capital M. Right? Okay. Minus u over u. That is 1. U over u means what? 1. Must be equal to minus u over f. What is the object distance for scenario 1? 12. Minus 12 over unknown f. So I understood when I apply the Lenz equation, I am getting two unknowns in one equation. I am getting two unknowns in one equation. Right? Then if there are two unknowns in one equation, there must be two equations at least to find f4 capital M or whatever. Then very clear, sir. We'll apply Lenz equation for scenario number 2 also. We'll apply Lenz equation for scenario number 2 also. Now scenario number 2 Lenz equation. If we apply Lenz equation for scenario number 2, apply Lenz equation for scenario number 2, case number 2. Case number 2. Case number 2. 1 over v minus 1 over u equals 1 over f. And then apply sign convention for scenario number 2. Then here convention, therefore sign is negative. Object distance opposite to the direction of light, therefore positive. Image distance is in the direction of light. In the direction of light, therefore negative. Minus 1 over v, minus 1 over u, minus 1 over f. If you cut all the minus terms, 1 over v plus 1 over u equals 1 over f. Right? So what shall I do? I write the second equation somewhere here. Right? 1 over v, 1 over v plus 1 over u. That is equal to how much? 1 over f. Again, multiply all the terms by u. If you multiply every term by u, we are getting what? We are getting 1 u over v. If you multiply all the terms by u, u over v plus u over u equals u over f. U over v means what? 1 over capital M. 1 over capital M. Right. 1 over capital M. Plus u over u means what? 1. U over u means what? 1 plus 1. Must be equal to u over f. Object distance, how much? U over 20. U is 20. 20 over f. 20 over f. 20 over f. Equation number 2. Right? Simple. Now I write this equation number 1 also near to this equation number 2. 1 over capital M minus 1. 1 over capital M minus 1. 1 over capital M minus 1 must be equal to minus 12 over f. Minus 12 over f. Equation 1. Minus 12 over f. My target is finding f. My target is finding f. Therefore, I want to remove this capital M. I thought of subtract equation 2 minus 1. Equation 2 minus 1. Subtract. Then we can write down 1 over capital M plus 1 minus the subtract minus 1 over capital M. Minus minus, therefore plus 1. I hope you understand. Right? 2 minus 1 minus 1 over capital M. Minus 1 means what? Plus 1. Plus 1 must be equal to 20 over f. 20 over f. 2 minus 1 2 minus 1. 2 minus 1 minus 12 over f. Minus 12 over f. Minus 12 over f. Right? Okay, then here what shall we do? 1 over capital M minus 1 over capital M cancel out. 1 plus 1 is how much? 2. 1 plus 1 is how much? 2. 2 equals common denominator. Simple if. There are different ways to get the answer. Simple if. Okay, simple if then 20, minus into minus means positive unit plus 12. Subject F, 20 plus 12 means 32. Subject F, 12 plus 20, 32 over 2. 32 over 2 means 16 centimeter. Right? That is the idea. How many of you understood question number 25 answer? 25 idea answer. Question number 25 idea answer. Now, if you draw the diagram, you should have an you should be able to decide the location where is the object. They told about virtual story. For a convex lens, there is only one virtual story when the object is between optical center and focal point. Then understand the location of the image. Image will be behind the object at the same side, upright, virtual, enlarged image idea. Then when we move the object further beyond, away from the convex lens, now object distance exceeding focal point. In that case, image will form at the other side, real image. Right? Since they mentioned both the images are same in size, for sure this virtual image is enlarged one. Since both the images are same size, this image is also enlarged, larger one than the object. This one is larger than the object, definitely. Object must be between focal point and center of curvature. This idea, no need, but I'm telling roughly. Then lens equation, and then thinking now. Based on the given data, you want to think some stories. The key story, if not key idea, is understanding both of them have same linear magnification. That is the key story. Understanding scenario 1 and scenario 2 having same linear magnification. Same linear magnification. If not, if you can remember, I gave this you idea. I gave you this idea now. What is, if you can remember, I gave this idea also now. Focal length how much? 16. Okay, 16. Okay, I told you. See, I gave an important point also. I gave you that if the object in front of a convex lens, I told you that if you now, I gave you theory idea like this. When the object is at equidistance from a focal point, okay? When the object is at equidistance from a focal point, then they will get same linear magnification. Okay, I gave a theory point last day. If an object is at equidistance from a focal point, they will have same linear magnification. Right? If you think the reciprocal in front of a convex lens, when you keep the object at two different locations, if you get the same linear magnification, definitely that object must be kept at equidistance from the focal point of the lens. Right? Then you can think. Initial object distance 12, now object distance 20 means focal length must be exactly between now 12, 20. This gap is how much? 8. This gap is 8. Focal length must be exactly in the middle of this gap. Therefore, focal is 16. Right? That theory idea, no? Theory idea, if you can remember. Hands up that this point I explained now. Got it, hands up? This point I explained just now, got it, hands up? How many of you? How many of you got this point, hands up? Anyone? Hands up if you didn't understand, hands up. I didn't understand. Hands up. I didn't understand. Then want to talk, man. Want to ask me if you don't understand something. It's very bad, huh? Now 26 badge is getting really worse. I don't know why. Not that asking the questions and not that much. I don't know why. It's not good. Because last 7 months only they are. Therefore, last 7 months only one girl is asked. I didn't get that point. Last 7 months only they are. Now only you want to ask your maximum questions. If not, sorry. Okay. Now can you remember last day I gave you a point, important point. I showed you. I proved also. I told you in front of a convex lens, when you keep an object equidistant from the focal point, you can keep an object, same object, right? A simple X to the right side of the focal point. If not, you can get the same object, simple X distance, left side from the focal point. That is the idea of placing an object equidistant from the focal point of a convex lens. Then I told you that the linear magnification of the image that you obtain in both the scenarios, right? If you keep the object simple X distance left right side from the lens, when you keep the object simple X distance right side from the focal point, your image will be somewhere here. If you keep the object simple X distance left side from the focal point, your image will be somewhere here, right? Both the images will have same linear magnification, right? Simply remember, I gave a point last day. When the object is placed, when the same object is placed equidistant from the focal point, remember the linear magnifications are same. This one's image height over this one's object height, right? This one's image height over this one's object height are same. Now this story what? This story opposite. Whenever you understand when the object is placed at two different locations in front of a convex lens, when an object is placed at two different locations of a convex lens, if you realized their linear magnifications are same, then these two objects must be exactly equidistantly placed from the focal point. These two objects must be placed equidistant from the focal point. This gap 12, this gap 20, right? Then these two gaps are same gap. Then 2x plus 12 how much? 2x plus 12 is how much? 20. X is how much? 4. Then what is the distance to the focal point? Focal length how much? Focal length x plus 12. Focal length x plus 12. That idea. Idea clear and some? Idea clear and some? Right? Now one is asking a question, so if the object is kept between optical center and the focal point, it doesn't mean that, sir, if the object is kept between optical center and focal point, it doesn't mean that object is always exactly in the distance f over 2, right? For a convex lens, it's not applicable. Huh? That story is not applicable for a convex lens. The student is asking, so if the object is kept between optical center and focal point, it doesn't mean that the object is always exactly in the distance f over 2. No, anywhere. In between optical center to focal point means it's like this new object can be somewhere here, right? That idea. Okay, right? Okay. Raise your hands. Whatever the theory that we learned, time is 10:05. Then tomorrow night, whatever we'll do a small question session. Theory finished. I will do a few more questions tomorrow. Then that is the plan. Just raise your hands. Whatever the story we learned today, right? Everything is crystal clear and so. Please ask doubts. These days, ask doubts. Okay. On the last 7 months, they ask doubts and learn as much as possible. Even one single marks matters for your A level. Now revision class. Yesterday I didn't do. The thing is revision class. Now I was preparing the tudes and all for theory classes. Right, you will get 3 tudes for this month. I'm posting tomorrow, if not Friday. Okay. Revision class I could not start yet. What shall I do? I will start next week proper revision class. Okay, I'm preparing the tude also yet. Want to do it properly, want to plan and do it. It should not be a theory class, so it should not be a kind of any other class, right? Therefore I'm preparing for that class. Therefore I could not do the class last week. First week I could not do definitely because I couldn't do any class in the first week, that idea. But definitely I will give a nice exposure, nice experience in the revision class. I want to do something big there, right? Working hard these days, okay? It's a different story. Different story now. Okay, now I think right today according to the plan we should start optical instruments today. I could have started optical instruments today, but it's okay, completely all right. Tomorrow night also we'll take that time and we'll do some lenses questions. This Sunday I will start optical instrument story. Okay, then I think all good, right? All good. Ask doubts, and now this is talk with me, because you are going to talk with me for maximum 7 months. Thereafter, you won't be able to talk with me also. Ne? Therefore, last 7 months, will work hard. You want to show your interest. You want to show me. If not, you want to act like you are interested. Then only I can also be motivated and I can also teach you. Right? I am ready to work with you unconditionally. I am ready to work with you. But if you're ready to work with me unconditionally, only we can go for a nice success. Right? So therefore, ask your doubts in your end, my end. I'm talking. That's how we'll do the class. If not difficult, if not very difficult, if not very difficult, right? In the question, if they don't mention what lens they are talking about, how are we assume whether it's convex or concave lens? Is it through the lens that converges are convex and which diverge are concave? Generally, yeah. Generally, the lens which are converging are convex, which are diverging are concave generally. But there are some exceptions. But now temporary, remember, lenses like the converging are convex, diverging are concave. That I don't temporarily remember. Okay. Sometimes if they don't specify the type of lens, they will give some hints like this, right? They will tell in a question, when object is placed at a certain distance, virtual image formed. When the object is moved here or there, real image is formed. That is only possible from a convex lens, right? Concave lens always gives a kind of virtual image, right? Likewise, there are ways to identify the type of image. We'll do few more questions regarding this tool and story. Then you will understand more. Don't worry, you will understand more. Don't worry. Okay. Normally, optical instrument section now. Lenses, we have to do lots of difficult questions. But optical instruments, only two convex lens, only two optical instruments, maximum only two convex lens. And when the object is at different locations, what will happen to the image? But when it comes to lenses, there is two convex, one concave, three concave. There are lots of complex questions in lenses section. If you are very thorough about lenses, optical instruments, ID fix, not a big deal. I think everyone understood the theory. I think we'll do more questions. Then, okay, right. Then we'll stop the class for today. Right. I have another class also. We'll stop the class for today and study will ask doubts. Okay. Okay. Right. Then I'm stopping the class. You want to reply to Ace Academy Suleiman sir. Okay. Don't you send to this video account. Any doubt you want to ask to that Suleiman sir account. Every time hereafter Suleiman sir reply. Okay. That idea. Okay.